Oh, okay, okay. Weer een backup. Hier, het handheld. Let's give a few minutes to people still to enter, because yeah, there were some very interesting drones, of course, flying in the coffee break room. So it's very hard to get people in here. Perhaps we could fly with the flapper drone upstairs and then into the room, and then people will follow it like this. Yeah, exactly. They should do the demos here. Ah, good, okay. I think it's nice to see. Okay, so in the interest of time, I would say let's get started. If we can see the presentation also on the screen, that would be fantastic. Like the presentation, could we have it on the screen? Oh, that's my mistake. Of course, you have to attach the HDMI cable again. So, yeah, my mistake. Apologies. Yeah, we have been switching it a bit. Yes, okay, all my fault. Anyway, so welcome at IMAV 2022. I'm Guido de Kroon. I'm a professor at aerospace here. And yeah, I'm very glad to see all of you this early already on this day. I know that there's also quite some teams actually not here because they're testing today. So for the greenhouse and also for the nanocopter challenge. But yeah, I'm very happy that you are here now. So welcome to Delft University of Technology. So you're in the what we call the aula, so the auditorium. This is actually one of the biggest halls, so it feels a bit empty if you're not with like 1,000 people. But yeah, it is a beautiful space, so I'm very happy we can welcome you here. What you see on the picture is the library. So it's one of the most iconic buildings of TU Delft, and it's actually just behind the aula. So TU Delft was founded in 1842 by this guy. He is King William II. So he founded the Technical University. And yeah, in the Netherlands we have a constitutional monarchy. So it's a democracy, and the king does not have any political, stature. But yeah, he's more a symbol of our nation. But it's not this guy anymore. That was a long time ago. So you must have noticed the flame in the IMAV logo, but also in the TU Delft. And it represents the fire stolen by Prometheus from the gods, bringing technology, knowledge and civilization to humankind. This is one picture of him. I saw another one where he was tortured by the gods for doing this. So yeah, apparently they didn't think it was a good idea that he did this. But that's part of our logo. And we have 25,000 students and 6,000 employees. And what I show here is one of the Nuna cars. So the students here, bachelor students, but also master students, they're really encouraged to engage in practical projects. And they have these, what they call dream teams, in which they compete in competitions. Very similar to you guys and girls, so that's, I think, very nice. And they do actually really amazing stuff. So this is a car with solar energy, and yeah, I think it's really impressive what students can do. And we always see that also at IMAV. So no pressure, but we expect, of course, a great deal also from you. So a little bit about the organizers, so that you know who we are. So yeah, we come from the Faculty of Aerospace Engineering. It's one of the buildings we're going to go to, this blue high-rise building. It has been founded in 1940, which is the year actually that the Germans invaded us, the Nazi Germans at the time. So I think it's a bit special year. But anyway, so it exists quite a long time. It's one of the largest and highest ranking aerospace faculties in the world. 2,800 students, 300 PhD students, and 200 staff. So it's really pretty big aerospace faculty. And we have many facilities. So it's actually pretty cool. We actually have a plane together with NLR. It's the Dutch Aerospace Institute. So we perform experiments with that. They have a fly-by-wire system, and we can, for example, plug in new control laws and things like that. So it's pretty cool. There's a big aerodynamics department that has an open jet facility. It's a big wind tunnel, so we can do very nice experiments there too. And what you're going to see tonight is the Cyber Zoo. So that's on the bottom. It's our flight arena. So it's 10 by 10 by 7 meters, and it looks pretty nice. But yeah, so it's not huge, but it's big enough to do some nice tests. So the organizers are from the Micro Air Vehicle Lab. So micro air vehicles reminds very much, of course, of the name of also IMAV. And so we really have as a mission to solve fundamental and also technological challenges of MAVs and to maximize utility and safety. And when you go to a small drone, inherently they get safer because the weight is lower, they also become useful in new cases, right? So, and this is what in the competitions we see, like for example in the greenhouse. Has anybody been in the greenhouse? Is there any greenhouse people here? No, okay. I can tell you it's very narrow. And so you have these tomato ranges, and there was one team that had a drone and it just fits. It's like a centimeter on each side, so I'm very curious how they're going to do, but it really promotes small drones. And so narrow environments, small drones are useful, and that's what we focus on with our lab. So we're actually relatively big lab as well. 9 scientific and technical staff members. We have 2 postdocs, 23 PhD students, and 6 engineers. And so we also really do practical projects with the engineers that are actually pretty impressive, I would say. I'm not doing those myself, so I can say that. But we really have a holistic approach to design, from design to control and AI. And so we really look at, okay, what does the drone need to do? And then we sometimes make a completely new design, and but also with the AI and control on there. And so I show a few examples. So one thing that was designed in the lab is the Delft Nimble. It's a flapping wing that can steer by changing the wing dynamics. And you just saw Maciej Karasek, who is the postdoc that designed this one. He also created the startup, and now he makes even more robust and nicer models. In the middle you see the Delftacopter. It's a hybrid drone that has like a helicopter blade and wings, and it can take off vertically and then transition. It's very hard to make the control laws for that one, but when it works, it's a very nice platform. So that in the middle, and on the bottom, it's perhaps hard to see, but there's a swarm of tiny drones that is able to find gas sources in unknown environments. So also to show that we really work on the AI for these small drones. Now, so who are we? So on the left, that's me. I noticed that I put the exact same suit and tie, so then you can recognize me today very well. Bart Remes, also co-organizing. Christophe de Wachter. So you have to remember his face because I'm going to ask you to find him in a picture in a second. So remember Christophe. Ewout Smeur and Salwa Hamaza. So, but we're helped by many people. And you can recognize them by the blue shirts or the red shirts. And we got a lot of help from the PhDs and postdocs. So thank you for that already. So a little bit about IMAV. So this is a picture where I want you to find Christophe, by the way. So anybody see him? Yeah, I see. Where is he? Can you? Oh yeah. So today we have a catch box. So whenever we interact with the audience, we throw this, of course, with engineers and computer scientists, this is very dangerous. Like we're better at typing than at throwing normally, right? But so I'm gonna start, a little bit safely. So you saw where he was? Yeah. Can you tell me where he is? Yeah, on that side. Whoa, oh, that's me. I should
Okay.
go away from you. Yeah. So if you should keep it like 20 centimeters. This is just to practice the.
Okay.
Yeah, and the mic is on the X side. Yeah, there. So where is he? No, no, no. You should talk into it, like.
I understand now.
No, you don't have to prove.
Hello.
Yeah, that's it. Yeah, yeah, yeah. Yeah, this is just to practice question and answer. So, can you see where he is? Where is he?
I think right there on the last.
Top left. Yeah, he's
Yes.
actually pretty obvious. Yeah. Yeah. It's because Christophe is so tall. And it's, okay. So yeah, it's a great picture because it was long, long ago in 2016. When yeah. Anyway, so IMAV history. So IMAV exists since 2004. And yeah, so that's a pretty long time ago when it concerns drone technology. This is the 19th event. I hope I counted right. Christophe, correct me if I'm wrong. But there's a few special cases. So in 2020, one IMAV was skipped because, yeah, COVID hit. And there was actually a double one in 2011. So we had even 2 IMAVs in 1 year. So that was completely crazy. We'll never do that again. But it's, yeah. So there have been many IMAVs. And yeah, I think it's nice to show you that many famous people in the drone world actually participated in IMAV in the past. So, for example, Petter Muren, you see a picture of him showing one of his tiny helicopters at IMAV. And he's, for example, the CEO of Prox Dynamics. They make the Black Hornet. It's this really tiny helicopter that is used by the military in Britain. Lawrence Meyer, so, and actually the whole Pixhawk team, so they participated in the competitions. And I guess most of you know Pixhawk. Who knows Pixhawk? Lots of people, yeah. Who knows paparazzi? Also lots of people, right? So anyway, yeah, sorry, you should also be there, of course. But Davide Scaramuzza, I think most of you may know him, very famous researcher. He was also joining one of the competitions. And Abraham Bachrach, he was doing SLAM with the drone at the time, and he's now CTO of Skydio. I don't know if you know Skydio, but I think most of you do. And actually, yeah, there's many more people. So also the Intel drone shows, the people that are behind that, they also, participated in IMAV. And you have Maciej Karasek, who also participated in IMAV. So it's very nice. So yeah, so no pressure also for you guys, but of course we hope in some years to put also your names on the slides. So what are the goals and mission of IMAV? Well, to further the progress of the science and technology of all aspects of MAVs. And I think that's one of the things that makes a conference also very nice. It's not just about AI or computer vision, or it's also about aerospace, aerodynamics, design, and it's where we all meet, because all these aspects matter. And if we screw up one of them, then the thing doesn't work. So this is really important. And the goals, I think it's nice perhaps to say that we really hope for an open exchange of knowledge and know-how. So at the conference, it's also open access, as I will emphasize later. But also during the competitions, we hope to push the state of the art with the competitions, but also provide a platform for young talents to learn. And it's much more about participating and also getting to know each other, and then about winning. So of course winning is nice, and you should try to win, but it's really not only about winning at all. It has to be accessible to new talents and cross-pollination between all these MAV-related areas. Now, and there are nowadays many competitions, of course. So from drone races to MB Zerg to whatnot, like grand DARPA challenges. And typically you can earn a lot of money. Here that's not the case, although we have very nice prizes for you if you win. But it's like more like a token. But what is the uniqueness of IMAV is that small size matters. So you see it in the scoring. If it's lighter, if it's smaller, you get more points. So that's what makes IMAV really unique. And so now, this was a long introduction, and now some practical information that you can actually use. So today, we're September 13. It's a lucky date. So we're at the conference center, so that's number 1 there. And at the end of the day, around, I think 4:45, so after the last presentation, some of the staff is going to walk with you to the Faculty of Aerospace Engineering. So that's number 2, where we will have the Nanocopter Challenge. So that's today. Tomorrow, there's the Greenhouse Challenge. This is an actual research greenhouse, and it's in Honselerdijk. Who knows Honselerdijk? Not many. I also didn't know it, and I live here. But it's like, you shouldn't say in the middle of nowhere, but it's like basically in the middle of nowhere. But we have buses for you, so I'll get back to the buses so that you can get there. On Thursday, there's the Package Delivery Challenge. So that's the outdoor competition in which some of you are participating, I think. And this is at Valkenburg, so some of you may have already seen it. It's an old airport that is now used as a kind of drone testing field. And on Friday, of course, we didn't want to book the exact same space to keep it exciting. We go to X. It's a building for sports, but they also have conferences there. So that's the 5th location, and there we will have a conference and the award ceremony. So this year, for the first time, we have one award ceremony at the event, and that's the Greenhouse Challenge. Because we really have like around 100 extra people visiting just for this challenge. And if you go to a competition, you want to see also an award ceremony. So that will be at the Greenhouse location. But all the other challenges, we take a little bit more time and we do the award ceremony at the end. Now, conference presentations. So this goes for some of you. So as the keynote speakers, we have and opening speakers, we have a headset. But for the other presenters, I think, because it's quite short, it's easiest to use the handheld mic, which is here. So you have 15 minutes. So I hope you prepared something like 10 to 12 minutes presentation, so that there's a little bit of time also for questions. And then you can try to be braver than I was and actually throw the catch box. For that. So there are some people also online. I don't know how many. It would be nice if many people are following this. But if you want to ask questions and you're online, then it's best to go to Zoom. So there's this link here. Of course, it's very easy to remember. So I hope that we will also put it on the website so that people can click it. And then you can actually ask your question with audio and video. And I don't know. I heard from the staff that it could be shown then or something. So let's hope that works. So about that. So we stream the conference on YouTube and the competitions as well. Only the outdoor competition we were not able to arrange live streaming, but all the other ones we stream live. The proceedings are published open access by TU Delft with digital object identifier and on the international page of IMAV. So if you have an article here, it will be open access, it has a DOI, it can be cited, etc. Now, most of you will have EduRoam, I guess, so then you have no problems getting Wi-Fi here. But should you not have it, then you have to SMS MAV Lab to this number. If you want to take a picture of that, that's a good moment. So, I'll give you a moment with that. Okay, so If this doesn't work, let me know, but it should work. So yeah, and then you have Wi-Fi here on campus, so until Friday. Food and drinks, so this is the most important part, of course. First, does anybody know what that is on the top right? Yes, can you tell me? Okay, I'm gonna throw this, shall we try this?
Okay, I don't know the name, but I know it's delicious.
It's delicious? Okay, yeah, good. That's the good answer. Yeah, so we call it bitterballen. It's really a poetic name, bitterballen. It's like bitter balls in English. But yeah, they're delicious, but watch out. So we had a Russian football coach in the Netherlands, and he was very mad because nobody told him that these bitterballen on the inside, it's very hot. So you shouldn't just put it in your mouth and then bite because you. So really bite it carefully. Yeah. So yeah. Anyway, I don't even know if we have that tonight, but yeah, anyway. So every day there's a lunch. So yeah, today there's a lunch here. Yeah. So basically every day there's a lunch. So at the greenhouse, outdoor location, things like that. Tuesday afternoon. So that's like when we go to the cyber zoo. There will be the competition, but we also have drinks and bites. Most probably bitterballen, but I cannot promise you that. By the way, the other one is stroopwafels. I'm pretty sure we don't have that one during the drink because it's very sweet. But if you don't know it, you should try to get them at some point during your stay. Wednesday afternoon at Tomato World, so the Greenhouse Challenge, we also have a drink with bites. And then Thursday evening, there's a conference dinner at Unmanned Valley. And a very big surprise in the evening. Yeah. Transport. So this is very, very important. So if you're sleeping now, watch out. So Wednesday and Thursday, we go really somewhere else. Of course, you can go there by yourself. So some teams have a car or something. Of course, you can go there. But I think most people probably will want to take the bus. And the bus departure is at 8 o'clock at the aula. So it's around this building. The bus will be waiting. So please come a little bit before 8 o'clock. Right? So I know it's early. So nobody likes early, or not many people. But so yeah, please be on time. On Wednesday, we come back around 7 o'clock. So that's still in time to have dinner. Watch out though with Dutch restaurants, they close a bit earlier than in Italy or something. So yeah, it would be good to go and find dinner around that time. Thursday morning, again 8 o'clock at the aula. So yeah, just remember 8 o'clock aula for these buses that go to the competition locations. Now I also had a slide on relevant factors in the Netherlands. There used to be a planned train strike, but that's not going to happen. So they reached an agreement, the train people and the government, and so no train strikes anymore. So thank you for that, and especially also nice for the people that have to travel. The weather forecast, so we're watching it every day, of course. In principle, we don't care that much, but for this day, obviously. So because Thursday, which is donderdag in Dutch, yeah, we have the outdoor competition. So what it says now, it's like 60% chance that there will be rain, but it also says 1 millimeter, which is not a lot, I would say. So yeah, let's just hope that it will be quite fine. So typically there may be perhaps a shower and then it passes. So let's hope for that. Okay, to end my talk, I would like to thank all our sponsors. So one sponsor is Dronisos, also the US Army, ONRG. We're also sponsored by Gemeente Westland and Robocrops for the Greenhouse Challenge, Unmanned Valley for the Outdoor Challenge, the AgTech Institute, so it's like the Agricultural Technology Institute at TU Delft, and the Robotics Institute have been nice enough to help us a lot. BitGrace, of course, and perhaps most importantly, Flapper Drones. So they have also been supporting, BitGrace has been supporting the Nanocopter Challenge as well, and also indeed Flapper Drones, by the way. So yeah, thanks a lot, because yeah, I don't know if you noticed, yeah, perhaps as a student you think like, yeah, 150 euros is a lot of money for registration, but actually thanks to the sponsors we could keep it so low. with all the activities and food and things during this week. So thanks a lot for that. And yeah, I'm really excited about the conference, looking forward to it. And with that, I want to close. So thank you for your attention. So, before we go on to a more interesting part, are there questions by anyone at this point? You can also always ask questions to the staff, to myself at another point, so don't worry. So, what we'll do, yeah. Sorry? Yeah, sorry, I didn't hear that, sorry. Okay, so yeah, then what we're going to do is we're going to go to the first keynote speech. So yeah, Yiannis, I'll put the HDMI in your laptop again. Oh. So yeah, we're very happy to today to have Yiannis Aloimonos with us. I found out today while reading the biography that he was born in Sparta, so I think that's very cool. I guess we all know Spartans, right? So yeah, and yeah, he first studied in Athens and yeah, mathematics, and then in Rochester, computer science, and now he's a professor in University of Maryland. And yeah, I think yeah, you're a really inspiring researcher. He is one of the founders of active vision, purposive vision, and so how intelligence is linked to taking actions in the real world. Of course, for robotics and drones, that's super relevant. And the last 5 or 10 years, he's been working a lot with this group on flying robots. And yeah, I think we're going to have a very interesting talk today about the bee robotic bee mind. So yeah, thank you very much, Yiannis, for accepting our invitation and coming here. And yeah, we're going to enjoy the talk.
Thank you, Guido, and thank you all. It's a real pleasure visiting your beautiful town and participating in your beautiful workshop. As Guido said, I've been working for a number of years in active perception, and Delft has established itself as one of the premier places in the world in the field of active perception. And I'm very happy to be here, and I hope to collaborate with you. Now, for the past several years, I've been working with flying mechanisms, drones, small drones, because it is much easier there to demonstrate the benefits of active perception. So we are not aerospace engineers, so we work with drones that you guys develop. And then we try to give them intelligence. Now, about a month ago, this book was published, The Mind of a Bee. I'm not going to go into details about what the book says, but basically, what the author argues is that the bee is a system just like we are. Is a system that thinks, that plans, that has memories, that communicates. It is a kind of cognitive system, but it is a minimal cognitive system. So what we are trying to do is build a robotic bee the size of a hummingbird, but functionally something that is performing the actions in the behavior of the bee. Not because we want to make a bee per se, but we want to build a minimal cognitive system Because in AI today, people are trying to build maximal cognitive systems, things that are human or superhuman. So we think it makes much more sense to scale down and build something which is intelligent and we can grow into more interesting architectures. So there are two basic themes in our work. One is something that I can call minimalism, where that basically means you want to solve a vision problem using the minimal amount of information. Now, you can understand that there is the maximal way of doing it, which is what is known in the field as SLAM. And there is minimum, whatever that may be. But then there is many other things in between, from the minimum to the maximum. There is a whole complexity hierarchy of systems. And the second topic, which is the main theme, is how do you develop sensory motor intelligence? How do you put together control and perception? Because control is done by a control people, and perception is done by perception people. But control and perception in living systems is one thing. It's not two things. And it is very fundamental to develop sensory motor intelligence. Why? When people study artificial intelligence, many of them go directly for language, the language that we speak. But our ancestors did not have language. We know that. Homo neanderthal, Homo erectus, Homo habilis, they didn't speak the way we speak with a combinatorial language, but they were thinking. They were planning. They were reasoning. How were they doing this? With sensory motor intelligence. So we need to understand that so that we'll be able to build language on it. Okay, so because this is going to be long, we're going to split it into 3 parts. First, I will speak to you about a minimalistic solution. I'll give you an example. Then we'll talk about control and perception. And then at the end, we'll take a tour through the mind of a robotic bee. Okay, minimalism. So let's say you want to solve the following problems. As you move, you want to find other moving things, what we call independently moving objects. If you're stationary, this is an easy problem. But if you are moving, the whole world is moving. And within that world, there are these other things that move independently. You want to find them. And then you want to be able to navigate in clutter environments, like a forest, or in that shared space. Or you want to go through gaps. There's a hole somewhere, you want to go through. We want to solve all these 3 problems. How? We are going to solve them by considering the uncertainty in optical flow. You all know what optical flow is. It's the projection of the 3-dimensional motion field on the image. And it's very difficult to compute. Let me show you something that is not very well known. This is the pattern by Uchi. Now, if you print this and you jiggle it, you're going to see 2 things moving. You may even, depending on your distance, see it on the screen by moving your eyes around the pattern. You see 2 things moving, not 1. And the reason that this is happening is that in the center you have many more horizontal gradients. And outside you have many more vertical gradients. So the normal flow, the image motion, which is perpendicular to the edges, which is something that you can compute easily, has many more values in the horizontal direction inside and less outside. Because of that, no matter what kind of algorithm you use to find the optical flow, you are going to have a bias. You are going to have a bias, and the bias, there will be an underestimation of length, of course, but there will be more underestimation in the direction of fewer measurements. So let me show you from another presentation. Give me a moment. So look, for example, at this input. Because you have bricks, right? You have this video. And the optical flow that you will get with this system that has these parameters, it has these errors, as you can see. These are very powerful networks. They have errors. Here's another algorithm. You see the errors, the red. You see the code here on the right. But if you find normal flow, which is the flow along the direction of the gradient, you don't have errors. So you can see here that kind of a result. So, okay. So let's continue here. We will solve these problems that I discussed, not by computing the flow, but by computing the places where we cannot compute the flow. For example, such places are occlusions. There's something you see in the first image, and you don't see it in the second image. There is no way that you can match it to find optical flow. So it's impossible to find flow there. So you have very high uncertainty. There's many ways to compute the uncertainty. Lots of ways. Here we train neural networks to do that. But the uncertainty is not only at the boundaries, because the boundaries will create occlusions. If you have fast motion, you're going to have blurring. Because you're going to have blurring, you're going to have uncertainty. If something is very close, the flow will be large or larger. And because of that, you're going to have more uncertainty. If there is a hole, it's going to be dark. You're going to have intensities that are almost the same, which creates uncertainty because you cannot match anything. So let me show you some results. So here's Chahat, and he's throwing an object. He's throwing an object. And here is this system from Intel that's trying to find that object. He's missing it. Another system, Midas, missing it. But with uncertainty in the optical flow, you get it. So here is again results from a few systems. Like number 4 is the so-called occlusion mask. Number 3 is a depth camera. And you see the results that are obtained. So the uncertainty finds the object. In the case of the ball, for example, the depth camera finds it. Midas, the various versions of Midas system miss it. The occlusion mask gets it a little bit, and the uncertainty solves it. So here is and the drone is dodging it. So here is navigating through a cluttered environment. And again, you can see the various different systems, depth camera, Midas, and so on, and what they provide regarding the spatial structure of the environment that you want to navigate. And you can see that the uncertainty is getting basically the spatial structure that is necessary for navigation. You have to do some diffusion so that you can group together all those pixels, as you see here. You find the free space, and you go into the free space. So finally, going through holes, most of the systems miss the holes. But here is the hole from the uncertainty. And then the drone can navigate. And of course, the shape of the hole doesn't really matter. Okay, so that was an example of minimalism. Now, minimalism is a part of the future, of course. It's not only for swap constraints. It's not only for the micro vehicles, because you cannot put much on them, so you need to be frugal. But it's also for the future. If you have self-driving cars that solve a number of problems, wouldn't you want cars that are cheaper, greener? That goes without saying. So, because if you make a self-driving car that costs $100,000, I can make one which is more frugal, and it is cheaper. And that can keep going until you optimize it. So it's not going to go away. Minimalism, and I'm saying this because the computer vision people are not thinking about this. They say, well, computer vision will give us a 3D model of the world. Now, planning, you can use planning and this 3D model to solve any problem. Well, but it's not like that. Are you making a 3D model? Sometimes, when you need it. Now that I'm looking at this, am I making a 3D model? Of course not. I don't even see everything. So minimalism is here to stay. And then, you know, there is obviously a very interesting theoretical question. I give you 1 million neurons. What can you do? The bumblebee has 1 million neurons. The honeybee has 850,000. And our neural networks, our everyday neural networks, have billions. One of the lessons from that book that I described to you, I mean, this research has been going on for a long time with bees, as you know, but this new work is more about learning, because the bees can learn many things, and they can transfer from one domain to another. So I give you $1 million. What can you do? You can have a complexity hierarchy depending on the amount of space. So one of the lessons is that you don't need many neurons in order to do things. You don't really need too many neurons to solve problems. This is the lesson we get from the fly. And computer scientists are figuring out ways on how you can create minimal networks. Okay? So we've been trying to develop those systems. This is an example of what we call the DVS camera or event camera, which is a topic that you guys here are working on also. And so our effort was to work with smaller and smaller drones, as you can see here. The smaller, the better. So this is where we are right now at this size, with this weight, this length, and of course, still much larger than the bee. So this is a story, so to speak, in this field, but I want to focus on what we did. From 2018 to 2021, we built this family of drones, like getting smaller every time. And my student, Nitin Sanket, who is now an assistant professor at the Worcester Polytechnic Institute, developed active vision approaches for robots, where basically you learn by moving the body. You learn with active sensors. That is, you learn by moving parts of the body with each other, and you learn by hallucination, by bringing memories of spatial locations. Now, from all this, I would like to focus on this thing that we did, because this is something that we collaborated with your own Guido de Kroon, where we developed a solution where, using DVS cameras, you can locate the drones by recognizing the propellers, because the propellers are rotating. It's the fastest thing. And so we did the learning in simulation. So you can see here, if you take a picture of the propeller rotating, there's not much you can do. But the moment you start seeing this with a DVS sensor, you can see everything. So we did the learning in simulation by, designing the propellers, using the appropriate systems, and it transferred perfectly to the real world, because you are looking at discontinuities. It's just a propeller that is moving. So here's another example where this guy is going to land on the moving thing. And it works on different real props, and etc. Good. Now let us move to our second and major topic, which is the hyperdimensional active perception. That is perception and control. Let me move directly to the gist of the argument, okay? Actions, what we do, are guided by prospective information as opposed to instantaneous feedback, because adaptive behavior has to deal with the fact that events precede feedback signals about them. So the delays in control pathways in the human is about 250 milliseconds. So you cannot just rely on feedback. only. The way to overcome this problem is to anticipate what is going to happen and use that to control behavior. So in other words, you have to make prediction. How are you going to make prediction and what are you going to predict? That's the question. You have to predict the vision. When you get out of your kitchen at home and you go left, you know exactly what you're going to see. You are predicting your vision. And if something is changed, like the wall changed color or there is a strange object, you immediately see that. Because you have predicted. You predict the sound. You predict the motor, the movements. These are parallel streams of signals. How are you going to make this prediction? How are you going to predict them all? Let's say you have some way, and you start predicting the vision, predicting the sound, predicting the control, everything. What if you have errors? If you have errors, how are you going to account for the inconsistencies between the streams? It's impossible. Cannot be done. Yet we do it. The neuroscientists have been telling us for a very long time that when the images come from the vision system through the thalamus, in the cortex, they emit sensory motor images. What are sensory motor images? So, we can predict if we can predict one thing only. So what is that thing? Or what could that thing be? Okay, so when you are interested in the mind, you realize that the mind is this amalgam. It has inside perception, planning, action, motor control, decision, knowledge, language. It has all these different things. Today, you can call them the different fields of AI. You can find them by going to departments and look at the professors and what the specializations are. So, all these people are trying to understand aspects of intelligence, but they speak different languages. Every field, you have to learn a language to get tenure or to get your PhD. You have to learn the language of that field. That's how you get respect. So like this reminds us of the Tower of Babel from the Bible for the Christians and the Jews, where the story goes that people try to make a tower very high and then God punished them by making them speak different languages. So they never managed to finish that project. So speaking these different languages between the fields of planning and reasoning and perception and control is creating problems for us. So in my view, we have to model the problem in such a way so that vision and sound and motor and all the signals, they are put together in one signal, just one. And that goes into your memory. And that's what you remember. and you can predict. And then you can split it back to the original contents. How can we do that? Well, there is a mathematical framework that was developed 20 years ago. It has this name, vector symbolic architectures. Another name is hyperdimensional computing. And you may even find other names as well. It was developed by a guy called Canerva. And it has taken quite some time for people to understand its power. But it's happening nowadays. In our days, there's a lot of excitement about this, and the publications in this field of hyperdimensional computing are rising exponentially. So basically, the way this works is everything is done with very long vectors, vectors of, dimension, let's say, 10,000. So if you are an image, you are represented with such a vector. If you are a video, you are represented with such a vector. If you are a motion, you are represented with such a vector. If you are a sound, you are represented with such a vector. If you are a plan, you are represented with such a vector. If you are a word, you are represented with such a vector. If you are a paragraph, you are represented with such a vector, and so on. Now, I've been saying if you are this, then you are represented with such a vector, but not all these problems are solved right now. For example, the problem of going from any image to such a vector is still an open problem. We can solve it under some conditions at this point, and we can solve it for the DVS because they are sparse signals. So this allows us to do two things. When it comes to intelligence and perception, there is always a dilemma. It is the relationship between signals and symbols. Where do the signals end and where do the symbols begin? Because I have images of you. These are signals. And then I say human, white shirt. These are symbols. There is a point as you analyze the signals that they are becoming like symbols. Where does that happen? This is a big problem. With hyperdimensional computing, you don't have this problem anymore. Why? Because these vectors are both signals and symbols. They are signals because you can take the Fourier transform, or you can apply filters to them. They are symbols because you can add them and multiply them. So in that space, you have addition and multiplication. You can take these two vectors and add them. The addition is the so-called consensus sum. What is consensus sum? Let's say the vectors are zeros and ones. So if you have more ones than zeros, then the result is 1. If you have more zeros than ones, the result is 0. If you have equal, then you randomly put something. That's the addition. Now, multiplication has many definitions because it's possible to define multiplications in many different ways. So one of the ways that we use is the exclusive OR. When you do multiplication, you bind the two things. You bind them together. So you take A multiplication B, and you find C, and that C has both of those guys inside. Imagine, in engineering parlance, this is like some convolution between two functions. So, of course, this has a number of properties, and you can use the multiplication, or what we call bundling, in order to associate things to each other, which you're going to need for recognition. And you can make records. You can do any kind of computation you can imagine. Okay? So these are some common vector symbolic architectures that people have been using. Another name is holographic reduced representations, and so on, but that's not that important for our... and so everything is done with those vectors, and you check whether they are the same using distances between those vectors, like the Hamming distance that people use, or other distances. So you have addition, you have multiplication, and you have permutation. Permutation, you just permute. These are the three operations. And so you can create sets, records, whatever. It's a universal model. So we would like to apply now this theory to the ego motion problem. And we have to bind. Now, before we go full speed into doing perception and control, we have to see if these ideas are working out. So we have to pick a simpler problem. And in this case, we want to bind perception with movement. Perception with movement, so that we can use the technique to discover the movement of moving things. And so we're going to use the DVS camera for this. As I told you before, this is what the camera sees. These are events. Okay. So a couple of years ago, we developed a solution for the normal flow. If you have a sequence of DVS images, you see on the left, you can create an image like that for a short amount of time, where you have, the blue, the red, the green, and what this shows to you is, over time, how the image is moving. Basically, it's moving that way, perpendicular to the edge. This is some representation of the normal flow. So, given a sequence of images, we can create this. And now, what we can do is we can bind this with the actual movement that is happening. In the x-axis, the y-axis, the z-axis, it doesn't matter. You have to take them all. Okay? And so there's an easy way to use hyperdimensional vectors to represent integers or real numbers of whatever you want. Okay? We don't have much time to go into the details, but it's not that hard. It's a bit harder to do the thing with images, and the way we are doing it in this project is by choosing a random permutation of rows and columns, and then the pixel in that image is R to X, C to the Y, I. In other words, the image is going to be the exclusive OR of all these values. and that is going to be the vector representing it. So now let me tell you in advance, the state-of-the-art algorithms that use billions of neurons in networks, they have 7 centimeters per second accuracy on data sets from the self-driving car reality. And what we get is 9 centimeters per second accuracy. But we have 270 times compression. We use very, very little space in order to do this computation. Anyway, so here it is graphically. From the images that you see here, we create a hypervector, what you see here, F, and then we bind that hypervector with a motion. Motion is this vector, let's say. And we bind it by taking the exclusive OR of the representation of this and the representation of this. Boom. That's our learning process. So these are all the hypervectors that we are learning from examples, and then what we can do is we can add them to make a set, because then they contain all of them. And then multiply this with our input, and then match with our memory so that we can get the best possible answer. Okay? So basically, we create hundreds of velocity bins represented as hypervectors, collect time images corresponding to each velocity, now form memories. So these memories are, all these example images, A1 plus A2, etc., and then you are binding it with the corresponding velocity, and you take that sum. And then for all velocities, you compute this quantity. The image that came in with the m vector and the appropriate velocity. And you find the result which is closest to 0. That's your answer. So, and we tested it on this data set, as you see here, and the results were very good. As I already described to you, they are a bit worse than the state of the art, but we can make them better by putting additional computation, okay? So this is the framework, how you can do inference with hyperdimensional numbers. So basically, the memory that we have, that we collect through our lives, whatever memories we have, they are the binding of the different senses with the motor system. They have everything together. And now if you have everything, you can do a lot of prediction by learning with LSTMs or transformers or other models. And you can predict. And after you can predict, you can split back. So you have two kinds of operations. The ones that bring together the different signals to create one. You use that one to do your business, and then you can split it back into the individual ones. So if you have an image, the image has a number of objects inside at different locations. At location X1, there is an object O1, etc. Now, if you use hyperdimensional vectors to denote the location, the image pixel, where the object is, and a hyperdimensional vector to denote the little window that contains the object, then your image is going to be this sum, x1 binding with O1, plus x2 binding with O2, etc. And now, if you have a sound, and there is a few people speaking, you have that sum of the different sounds. And each one of those sounds is the binding of different auditory representations involving scales, frequency, etc. So if you have an algorithm where I give you a hypervector and I say, split it down to a sum of this kind, if you can do it, then you have done segmentation of the image. And with the same algorithm, you can do segmentation of the sound, because it's the same problem. You are working with these hypervectors, and you don't care whether the hypervector came from vision or whether it came from sound. So in principle, and this is something we would like to demonstrate, you can have the exact same algorithm, no change. Gets us input an image and gives you image segmentation, or gets us input with a sound and gives you sound segmentation, splits down to the individual sounds. Looks like brain computations are in that kind of manner. So, and we are ready now to develop sensorimotor memories. Of course, in developing sensorimotor memories, you know, this is, again, not a trivial problem. You don't just throw them there. You have to structure them in some way, okay? And memories of what? Of what you see. And what is it that you see? In the most general case, is action. You see an action. Let's say you are a human, you look at other humans. If you are a bee, you look at other bees of the world. You see actions. And actions have a place in the Chomsky hierarchy. So I don't know how much familiar you are with this kind of literature, but if you have a simple task, something that you can do with one hand, then this can be represented with a regular grammar, which is equivalent to a finite state automaton. But if you do something with two hands, then a regular grammar is not enough. You have to have a context-free grammar, which is equivalent to a push-down automaton, which is a finite automaton, but it has also a stack where you can put things in and take them out. So there was a paper recently from DeepMind where they have done an empirical analysis of transformers and recursive neural networks, and they found out that the transformers can only deal with regular sequences. They cannot deal with more complex sequences. Only the recursive neural networks with a stack or tape. So we want to use those ones for prediction. Okay? So to recap our second topic, I have to move fast now. You see a dog, you hear gav, gav, you see the word dog, you hear the word dog. All of this, they're going to end up in the same vector. Now, if you want to integrate a system, and you know, I really believe this, and I want to be your friend, because from all the communities, you are the only ones that you are really interested in the integration of the system. you want to integrate all the components. Because other fields are not doing this really. So in order to do integration, you need the different components to speak the same language. So I believe hyperdimensional computing is the way to go about this. So now let's come to the big brain. This is the big brain from a micro CT. And you can see on the left and right is what you can call the equivalent of the visual cortex in the human brain. These are the lamina, the medulla, and lobula, which is hierarchical neural networks for doing representation of visual information. And the red structures that you see up top are the so-called mushroom bodies with the canyon cells. And it looks like signals go there also from the taste sensors. At the top, you see the ocellular networks that are dealing with optical flow-like quantities and the spatial structure. And then in the middle, you have the so-called central body, okay? This is the only structure that is unpaired. All the other structures, there is one on the left and one on the right. But this one has only one. And you have the photocerebral bridge, which is some sort of compass. And then you have the fan-shaped body and the ellipsoid body, where basically they think that navigation happens and semantic memory, because you need landmarks for navigation. So the recognition of objects happens, they think, in that. So, as I was telling you before, to achieve minimal cognition, you have to have a set of visual capabilities, and on top of that, episodic memory, what happened during the day in your life, semantic, recognizing objects and actions, and procedural memory that has the actions that you do, models of action. So this is from the book of Buzaki, that believes in action as being the most fundamental component of a system. And he argues that navigation gave rise to memory, first by doing egocentric things with dead reckoning, and then later by doing allocentric things, by developing landmark information and representing the space in the form of a graph. And that gave rise to both episodic and semantic memory. And so, as I told you, we've been trying to build that kind of minimal cognitive system. But we want to do it in such a context so that we can do something useful. So the way we thought about it was to build a beehive with little drones that could, in principle, navigate, find flowers, touch them, and keep doing this so that they can artificially pollinate the scene. Why? Because it's possible that the bees may disappear because they have all kinds of diseases. So while the scientists are trying to save them, we wanted to investigate the possibility to find out, can we do it artificially? Of course, you have to imagine that the bees right now are too big, but I'm pretty sure in a number of years from now, your community will have built very, very small mechanisms. So this is the beehive that we have built. And it has this so that it can anchor from a tree. And it has drones that are held with electromagnets. These are the drones that we are using. And here it has perched. And now they are coming out and searching for the flower to touch. Now, it turns out finding flowers is a pretty elaborate thing. And the bees use also ultraviolet, so you can do obstacle avoidance when this guy is threatening, and so on. Okay, so this is, so to speak, the diagram of how that system is working. Pay attention to the tasks, because here's the trick, okay? Here's the whole point. If this is the robo-bee that finds flowers and does something, if I go to the tasks and change something, then I have all of a sudden a bee that is going to inspect bridges. I go change something, and I have all of a sudden a bee that is searching for policemen. I go search something, and I have, you see my point. So you have the task space. What is the system doing? Very important for intelligence. That's what you have to start with. What are you going to be doing as a system? Then you can figure out the rest. So we developed all these capabilities, like from kinetic stabilization, segmentation, avoidance of obstacles, homing, static landing, and the blue stuff is just for a single bee, and now if you have multiple, then you can have tasks that you have to do together, okay? So these kinds of things every drone should have. And then depending on the specialization, you may have to put in additional behaviors. So okay, I'll try to go fast. So what is our point? Our point is, look, suppose you have, suppose you build a robot that makes a Greek salad. And it's very good. You can find tomatoes, cucumbers, however they are, cut them, mix them. It works fine. Where is the intelligence? When you're finished and you look at this, it's not different than a thermostat. It's a special program. You can see it. Where's the intelligence? The intelligence is in the mind of the programmer who wrote that program. So that's what you want. You want to have intelligence. You give a system a problem, then the system has to generate the program that will solve this problem. Then you give the system another problem. Now the system has to generate the program that will solve this problem. That's intelligence. So the system is more like a compiler or an interpreter, where you give it a goal, and then it goes to the task space or action space, and through some planning mechanism, it tries to put together the individual primitive actions that the system knows so that it can synthesize the goal. And that is happening in tandem with perception and episodic and semantic memory. That is, I believe, how the bee is working, because it's very intelligent. The bee is solving problems. So how do we know that the task space has primitives? Very quickly, I'll tell you, because we don't know what the bee is doing, really, but we know what the humans are doing. And 100 years ago, Frank Gilbert with his wife, they looked at thousands of workers, and they found out that they are doing one of 15 different things: search, find, select, transport, like the hand is moving empty to pick up something, or the hand is moving with something. So if you look at somebody doing something, is doing one of those things. These are the primitives. And so transport empty, hold, release, position, preposition, grasp, etc. So if you have somebody that is opening, the fridge to get milk and make a bowl of cereals, you have these there bricks. Transport empty towards the plate. He goes to pick up the plate. Grasp plate. Transport loaded, a plate on the table, and so on. So you can translate now from vision language to verbal language. And one of the things that we have learned over a number of years is that there is syntax in action. And because there is syntax, I go quickly. These are productions of the grammar that will produce this action. Because there is syntax, you can write programs. Actions are like little programs. Okay?
We learned actions of manipulation by processing videos from the internet and represent them in a form such that a robot can perform.
I'll be finishing in a couple of minutes, okay? Here you see how you can use this framework to learn from videos how to do something by building the parse trees of the activity. And now the robot can take the things that you can see on the upper left and perform the same action. Okay? So we can write little programs for every action. And these programs have these primitives, like grasp and move, etc. Leibniz was looking for an alphabet of thought, and he talked about primitive concepts, because everything you understand it in terms of something else, and that something else in terms of something else, and then something else. Then you have to stop somewhere. Where do you stop? You stop at a primitive concept that you understand in terms of itself. And linguists have thought about them 100 years ago, the primitive concepts. And the way they tried to do it is they said, if in two languages you have a primitive concept, then it has to mean exactly the same thing in the two languages. So they looked at 28 languages and they found the words that mean exactly the same thing. And these are the words that they found. These are the primitive concepts. Of course, this is only necessary and not sufficient. In other words, you can have two things that mean exactly the same thing, but they are not necessarily primitive. So the real primitives are a subset of this. Okay? So we have been designing this programming language called AL, so that we can write actions, and we are developing 4 different compilers. This is my last slide. The VALC, Video Action Language Compiler. When you look at the video, and you are going to generate the action that is taking place as a program. And then you can take that and use it in a video action language debugger that you can use for augmented reality. Or you can have a motor compiler. You know, all over the world there are people writing trying to solve the same problem with different robots. And they end up doing different things. Why? We should all have the same program. These robots are doing the same thing. And then we should have compilers that take this program, and then if you want to run it on this robot, then it will get you the code for this robot. You want to run it in another robot, it will get you the code for another robot. But that is somewhat complex because it involves perception as well. So the thing to remember, minimal cognition. You can have a system with basic capabilities, visual and otherwise, and with semantic, procedural, and episodic memory. And then you have the task space organized around the primitives and a way to put the primitives together to generate any kind of action. Okay? And that's the end of my talk, and I want to thank you, and I wish you good luck with your research and with the competition. Thank you. Sorry for running 3 minutes over.
It's okay. It's very interesting. Thank you very much, Yiannis.
So I'll be here all day today, and if you would like to discuss any of these topics, I will be very happy to.
And I think we have time for a few questions, if there are any in the audience. Don't be shy. While you think of it, I have one question, Yiannis. So I think it's really fascinating, the idea of...
I can't hear you, my friend.
Oh, sorry. Yeah. Also, I'll come stand next to you.
Okay.
So the uncertainty in optic flow,
The
I think is very
yes.
interesting. I was wondering, in one case, the uncertainty of optic flow indicates the obstacle, but in the gap, it indicates the gap. So I was wondering, how does it then know or learn when uncertainty is good, like the gap, you want to go through it, and when it's bad, that you want to go around it?
That because it also knows about the closest obstacle kind of thing. Okay?
Okay, so closeness is...
right. So by combining this, you can get the answer to what you are asking.
Okay, so it's combining with the flow as well.
Right.
Okay. Is there still any question from the audience? Because if not, then I propose that we have a break and you can go to Aloimonos, Yiannis, and ask it there. So thank you again, Yiannis, for a great talk.
Thank you. It was a pleasure. Thank you, guys.
So we now have a break until 11:30. So we go back to the foyer where there's coffee and tea, and there's also bitcrates and flapper drones with the stands.
Someone told me long ago there's a calm before the storm. I know it's been coming for some time. When it's over, so they say, it'll rain a sunny day. I know, shining down like water.
serca, hej, hej, hej.
She was more like a beauty queen from a movie scene. I said, oh my, but what do you mean? I'm the one who we dance on the floor in a round. She said, I'm the one who we dance on the floor in a round. She told me her name was Billie Jean, and she got the scene. And every hair turned red eyes a dream of being the one who we dance on the floor in a round.
People always told me, be careful what you do. Don't go around breaking your girl's hearts. And mother always told me, be careful what you love. Be careful what you do, cause a lie becomes a truth. Billie Jean, it's not my love. She's just a girl who claims that I'm the one. But the kid is not my son. She says I am the one, but the kid is not my son.
Days and 40 nights I was on her side, but who can stand when she's seen the man, her schemes and plans? Cause we dance on the floor in a round. So take my strong advice, just remember to always think twice. She told my baby with dancing tree, and she looked at me and showed a photo. My baby cries, eyes were like mine. So we dance on the floor in a round.
People always told me, be careful what you do. Don't go around breaking your girl's hearts. She came and stood right by me, then the smell of sweet perfume. This happened much too soon. She called me to her room. Billie Jean, it's not my love. She's just a girl who claims that I'm the one. But the kid is not my son. She says I am the one, but the kid is not my son.
Talking away, I don't know what I'm to say. I'll say it anyway. Today's another day to find you shine away. I'll be coming for your love, okay? Take on me, take me on.
me, some boys hug me. I think they're okay. If they don't give me proper credit, I just walk away. They can beg and they can plead, but they can't see the light. 'Cause the boy with the cold hard cash is always Mr. Right. 'Cause we're living in a material world, and I am a material girl. You know that we're living in a material world, and I am a material girl. A material girl. Some boys romance, some boys slow dance. That's alright with me. If they can't rise my interest, then I have to let them be. But some boys try and some boys lie, but I don't let them play. The only boys who save their pennies make my rainy day. 'Cause we're living in a material world, and I am a material girl. You know that we're living in a material world, and I am a material girl. A material girl. Boys may come and boys may go, and that's alright, you see. Experience has made me rich, and now they're after me. 'Cause everybody's living in a material world, and I am a material girl. You know that we're living in a material world, and I am a material girl. A material girl. She was a working girl, north of England way. Now she's hit the big times in the USA. And if he could only hear me, this is what I say. Honey pie, you are making me crazy. I'm in love but I'm lazy. So won't you please come home? Oh, honey pie, my position is tragic. Come and show me the magic of your Hollywood song. You became a legend of the silver screen, and now the thought of meeting you makes me weak and I need. Honey pie, you are driving me frantic. Sail across the Atlantic to be where you belong. Will the wind that blew her boat across the sea kindly send her sailing back to me? Please, now
rushing springs to life, opens up one eager eye, focusing it on the sky. As night and night, red balloons go by. 99 Decision Street, 99 ministers meet to worry, super flurry. Call the troops out in a hurry. This is what we've waited for. This is it, boys. This is war. The president is on the line. As night and night, red balloons go by. 99 nights of the air, by super high-tech jet fighters. Everyone's a superhero, and everyone's a Captain Kirk, with others to identify, to clarify and classify, scramble in the summer sky. As night and night, red balloons go. 99 dreams I have had, everyone in red balloon. It's all over and I'm standing pretty in this dust that was a city. If I could find a souvenir just to prove the world was here. And here is a red balloon. I think of you and let it go.
Welcome back, everybody. So now it's my honor to host the first session of the IMAV conference, which is the guidance and control session. My name is Ewout Smeurs. I'm part of the organization. I work at the MAV lab as an assistant professor. And maybe a quick announcement before we start with the session, and that's that the papers are already online on the imavs.org website. And they are listed in the order of presentation. So, because the time is quite short, without further ado, I want to introduce the first speaker. It's Marco Martinez from the Instituto Politécnico Nacional from Mexico. So, the floor is yours.
Thank you. My name is Marco Antonio Martinez Ramirez. I'm going to give a quick talk about the paper called Lateral Guidance and Control for a Fixed-Wing Aircraft, written by Hugo Rodriguez Cortez, Juan Jose Corona Sanchez, and by me. Well, I'm going to present a real quick introduction, then I'm going to explain some details and considerations for the lateral directional dynamics and kinematics. Then I'm going to detail the control design, and at the end I'll show numerical simulations. Well, unmanned aerial vehicles are used in a wide list of applications, such as meteorological monitoring, precision agriculture, and ground vehicle tracking. In this work, we consider a 4-channel aircraft. That means that has the 4 basic control inputs, the engine, and the 3 basic control surfaces. Well, the aircraft dynamic model is well known. It's usually divided into 3 equations for the longitudinal dynamic, and the rest of the equations are the lateral directional dynamic. we consider that there is already a longitudinal controller, so we only use the lateral dynamic equations. And we also consider the coordinated turn condition. That means that the lateral coefficient 40 is equal to 0. Also, the side slip angle is 0. Well, the kinematic model is given by the first 4 equations, where x and y represent the aircraft position in the Cartesian plane. And the azimuth angle is given by the yaw angle minus the side slip angle. And the aircraft path angle is given by the pitch angle minus the angle of attack. And C1 and C2 are given by these combinations of sinus and cosinus. It's hard to work with all of that values, so we use some considerations. Some of you may think that are generous assumptions, but if we don't use them, it's little to do with these whole equations. So we assume that the side slip angle is equal to 0 and the angle of attack is really small, almost, well, not as small as 0, but really, really small. Under this assumption, the whole model is given by these 6 equations. Now, the control objective is that given 2 waypoints, we create an imaginary line that connects to those 2 waypoints, and the objective is to bring the aircraft to that imaginary line. In order to achieve this, we consider our inner-outer control loop, where the inner control loop has the super twisting controller, which is known to have finite time convergence. So we're going to focus on the outer control loop, where we define the references that then we feed to the inner control loop. These references are the roll angular velocity and the yaw angular velocity. So we work with these equations. In terms of the errors, we have the first 4 equations. So we have the super twisting. So we can consider that the errors are 0. We also select the coordinated turn condition. So at the end, we have the last 4 equations. And as you can see, we only have one control input, the PT. The main problem with those equations is that they don't consider the configuration space of the yaw angle, which is the unit circle. So we take that configuration space and we represent it in a matrix. So the kinematic model in terms of that matrix is given by the 3rd, 4th, and 5th equation. So first we solve the easiest problem. We have a reference in the y-axis. Basically, we have an infinite line that is parallel to the x-axis. Well, we define the error as till the y equal to y minus the desired y. So the attitude error through the matrix is given by the only equation that we have there. So in this case, the velocity is given by the first equation. Since the objective is to command tilde RC to the identity matrix, we can separate the rest of the equation into those 2 equations. Well, we want to command the lateral position. So our virtual control input, it's the sinus. We know that the sinus take values from -1 to 1. So we use the hyperbolic tangent. From that, we can construct a new matrix. And well, that's the easiest case. In a more general case, we use an auxiliary axis system, which needs to have the new x-axis parallel to the line that is no longer parallel to the north. So in this general case, the position, the aircraft position is given by data rotation matrix and the position in the northeast down system. Well, under this axis system, the velocities are given by the first equation. However, we define the attitude error now like this. And it's a little bit more complex, not too much complex, just we add another rotation matrix, which is the desired orientation. It's parallel to the line that connects the waypoints. So the velocities can be expressed as that last equation. As you can see, that seems a lot like the easiest case. The lateral error is given by the first equation. We use some rotations. And again, we can separate the velocities into x and y, but in the auxiliary system, we have almost the same form as the easiest case. So again, we use the sinus signal. It's all almost the same as the easiest case. And we define the correction matrix. In this way, the aircraft, what it does is to follows the line, and after the error is 0, orientates the aircraft to keep that attitude. Well, the error dynamics for the matrix are given by the dynamic model. And we propose that control law. Again, from the dynamic model, we select the zeta in that way. And taking its time derivative, we have the fourth equation. If we select correctly the control input PG, we can get to the last form, which we know is, it has a stable point at 0. Now, I didn't detail a lot because of the lack of time, but we have our simulation platform, the Telemaster. We used a UDP communication between MATLAB Simulink and Explain in order to create our simulations. We use these values. The inertial values were took from a CAD model, and well, as I mentioned, we consider that there is a longitudinal dynamic controller that holds those values, and the gains in the controller, well, or low control are these. So these are the results. At first, the aircraft takes off, following the wrong way, and approximately at the second 45, we activated our controller. So when the aircraft is within 150 meters from the desired last waypoint, it goes to the next. We make the aircraft to follow a square path. And basically, the results are this. This is the lateral error position. As you can see, converge asymptotically to 0. Those values are for the wrong angle, the roll angle. And it takes values about 0.6, which is about less than 40 degrees. It's something that the aircraft can achieve. Now, the attitude error, as you can see, also converge asymptotically to 0. And the coordinated turn condition, it's oscillating a lot, but there are low amplitude oscillations. So it's no problem. So in conclusion, we propose a guidance algorithm. We consider the configuration space of the yaw angle, and we show numerical simulations. At the moment, we are working on the physical implementation on our aircraft. We count with an autopilot, the Navia 2, that has enough sensors to make the physical implementation possible. So that's all.
Thank you very much, Marco, for this very nice presentation. Very cool to see that you did the actual, or that you're working on the actual experiments. Are there any questions for Marco? I see a question there. You want to do the throwing, or shall I?
Okay. Sorry.
Nice throw.
What is the expected weight of this aircraft?
Well, it weighs about 3 to 4 kilograms. Okay.
Question there.
For the guidance, you have presented the following of a line. Have you tried or studied the following of a circle, for instance? And is there any chance that you have a static error if it has to keep turning? Or do your control, is it compensating for the circle? And
excuse me, I didn't understand.
I mean, when you are following the line, you can see that it's removing the static error and you are exactly on the line, but it's a straight line. Is it the same if you follow a circular pattern or not?
Well, yeah, we could follow a circle if we consider, where is, yeah, here. Well, for the line, we consider that our matrix RCZ, it's constant. We can follow a circle. If we consider that is no constant, we have to take its time derivative. But yeah, it's possible to follow a circle.
Then I also have a question myself. Did you also take into account wind or simulate the simulation with wind and see the effects?
Yeah, no, the simulation don't consider wind, but that could be get into the inner control loop. Yeah, that's where we would consider that all the disturbances.
All right, thank you very much. Then I think it's time to switch to the next presenter. Let me get my paper. Let's thank Marco one more time. The next presenter is Zeynep Bilgin from the Middle East Technical University in Turkey. And the paper is a collaboration also with ENAC from Toulouse. So without further ado, the floor is yours.
Hello. Hello, thank you for your kind introduction. I want to introduce my co-authors. Dr. Bronze is from ENAC, France, and my PhD advisor, Dr. Yarucuk, is from Technical University of Munich. He is not here today. So let me quickly go over the outline of my presentation. I will start with a brief introduction of our methodology and then talk about our experimental setup and deliver my results and conclusions. So path planning and guidance efforts are very well studied in UAV field. I divide the existing approach into two main categories. First one is optimization problem-based approaches. Here, the problem is defined as a large optimization problem with constraints, and it can be solved to generate paths. And the second approach is artificial potential fields. The beauty of artificial potential field approach is in its simplicity and easy implementation, very intuitive, but it suffers from a problem that is the local minima. So also there are some methods to encounter this problem, and one of them is employing harmonic potential fields. Harmonic potential fields guarantee global convergence and generate well-behaved, smooth robot trajectories. A very popular example of a harmonic potential field comes from our daily life, which is the fluid flow. So if you can imagine a river flowing and the rocks in the river, the water just flows around them without causing any collision. So this fluid flow around obstacles can actually be used to guide vehicles in difficult terrains. The analytical solution for this approach exists for simple shapes like cylinders, which is not quite practical. And there is a numerical tool to solve the problem around arbitrarily shaped object, which is called the panel method. So panel method is commonly used in aerodynamics and fluid mechanics domain. And in case you are not very familiar with the method, I'm going to briefly tell you how it works. So you divide the surface of an object into small line segments called panels and place a elementary flow element on each panel. And then using a simple relation, the velocity at any point in a region can be calculated. What we do is we calculate the velocities on the surface of the object and then equate the normal components to zero so that the flow cannot go into the object. This results in some set of linear equations. And solution to these linear equations gives us the ability to calculate velocity of any point in a region. So what we do is, given the location of the obstacles and position of the vehicle, we can calculate the flow velocity at this given instance and given point. Then we normalize and scale this flow velocity and turn it into a desired velocity for the vehicle. Then, using the automatic flight controller, we change this desired velocity into heading error and then roll angle error, and the desired roll angle is fed to the vehicle. And through this feedback loop, we guide the vehicle with this desired velocity obtained from panel method. For our experiments, we use the fixed-wing platform with Paparazzi autopilot system. In our previous works, we worked with quadrotors, which was much easier compared to this fixed-wing setup, because the fixed-wing aircraft cannot go sideways or backwards, and it suffers from a turn radius limitation and minimum speed limitation. So it was a more challenging platform than our previous studies. So let me show you our simulation results. So for all of the scenarios in this study, we choose 5 points, and the vehicle travels between these 5 points in a circular fashion. And our outdoor experiments are conducted in south of France, Muret. In the right side image, you see the satellite view of our flight test region. So for these experiments, the aircraft starts at a standby position just outside our flight arena, and then it is tasked to go to the point A, B, C, D, E, and then keep circling in that fashion. So these magenta things you see, squares and rectangles you see, are the objects, obstacles. So we couldn't physically insert such huge obstacles, so these are more like no-fly zones. And this red line is the trajectory of the vehicle, and these little black arrows are the calculated desired velocity by our algorithm. Please don't let this red line fool you, because this algorithm actually does not generate a trajectory for a vehicle to follow. Instead, what we do is we calculate a desired velocity at each point, and we know that this velocity is going to take our vehicle to a goal position without collision. And we have this very special velocity available at any point in the map, so wherever the vehicle goes, we know which velocity to feed it so that it won't hit any objects and arrive at a destination. So in this image, you see our result from a real flight with the previous arena. So this is a really tight arena for our fixed-wing aircraft, and around the point C and the rectangle object, you can see that we are at the absolute limit of our turn radius, but still the buildings repulse the vehicle so that the collision is avoided at that position. And our second flight scenario is a much larger arena. This is almost twice as large. So all the equations are non-dimensional, so it's really easy to scale this method to larger or smaller problems. In this case, you see, since the arena is much larger, we don't have any issues with minimum turn radius. But the interesting thing about this arena is you can see the odd-shaped obstacles. One of them is a concave obstacle, and you can see other weird-shaped obstacles. So panel method is really strong when it comes to these arbitrarily shaped obstacles. We can calculate flow around almost anything. So let me deliver my conclusions. For this study, we used panel method-based guidance for a fixed-wing platform, and we tested it in both simulation and outdoor flight tests. And our experiments indicate that panel method-based guidance works well with this fixed-wing platform, even in the face of these flight envelope constraints. And for our future work, we want to improve this method even more to address this envelope constraints even better. So this concludes my presentation. Thank you.
Thank you, Zainab, for this very nice presentation. Are there any questions from the audience? Yeah, I see here.
Thank you for the nice presentation.
Thank you.
I was wondering, computationally, how much computational effort does it cost to calculate the vector for a single point, for example, where you are?
Thank you for that question. It's actually a very good question, and one of the strengths of panel method, because it's only a matrix multiplication, so it's super, super fast, and we calculated at each time step. We were able to do it for an arena with 6 or 7 obstacles around 200 hertz, so 2000 hertz. So it's insanely fast. I mean, we cannot feed that information to our vehicle at that speed. So that is definitely not the bottleneck for our algorithm. It's really fast.
Would it be possible to calculate that on board? Would it be possible to calculate this information on board of the vehicle?
Yeah, it would be possible. It's possible to calculate on board, but you have to know the position of the obstacles beforehand. That's the only constraint.
Yeah, thank you. Are there more questions? Yeah, I see one there.
Well, thank you for the nice presentation.
Thank you.
Yeah, I was wondering if the panel method is done in the 2D plane, as you see the object as a 2D entity, or it can be extrapolated to the 3D panel method.
Again, a very, very good question. So what we do here is we consider the obstacles in 2D planes, and we say that, okay, the vehicle is flying at a constant altitude, and we take a cross-section, and these are the 2D obstacles. But it can be extended to a 3D case. However, we thought this altitude approach and taking cross-sections is much easier than trying to do a 3D meshing and 3D panel method. So we are using this in 2D right now.
Actually, I have one more question myself. Can you say anything about the optimality of the trajectory that follows from this method?
That's, oh my God, so many good questions today. Thank you. Actually, we don't know anything about the optimality of the trajectory generated. We know that the convergence is guaranteed. I mean, we are going to reach our goal position no matter what, and obstacle avoidance is guaranteed. But we don't know whether this path we are following is like shortest or the fastest or most energy sufficient. We actually have no information on that.
All right, thank you very much. Let's thank Zainab one more time. And then our next presenter is all the way from Korea. His name is Taehyun Kim. I hope I pronounced that correctly. And he's from the Chungnam National University of Korea. Well, Taehyun, the floor is yours.
Yeah, that's right. Thank you for introduction, Chairman. Checked. Okay. It's time to travel. Okay. Good afternoon, everyone. Thank you for coming here today. My name is Taehyun Kim from Chungnam National University in Korea. Today's my title of my subject is Reconnaissance, Target Grouping, and Assignments. Consider first severity for UAV swarm. Okay. I will introduce my background, motivation, and objective my study in introduction section, and I present my process of our proposed task assignment with consider the target grouping and the task assignment with using the Hungarian algorithm. And in simulation section, I will explain. We analyzed our proposed target algorithm compared with just consider the minimum distance case. And after the conclusion section, I will summarize my presentation with conclusion and our future works. Before the introduction, why should we consider the fault severity? In these days, the UAV, the unmanned vehicle industry required complex operation in various fields. So it leads to an accident increase during the missions. As you can see, these graphs are it's not worked the laser. These graphs here are survey reports on unmanned vehicle industry in Korea. As you can see, the frequency of faults and fault severities are different. It depends on the equipment. So this result leads to if the fault severity is considered in task assignment, maybe it can make the operation will be more efficiency. This video is a fault occurred situation when I was testing a small swarm flight test. There's one reader UAVs fell, and other rest UAVs were stopped when the reader UAVs fell. Why they are stopped? Because I didn't consider it. I didn't consider the after task assignment when the fault occurred. So if a fault occurs during the flight, maybe the task assignment condition will be changes. So these reasons, our research. Our research objectives are set as follows. We designed the task assignment algorithm. We consider fault severity, and severity which increase the efficiency of the mission performance when the fault occurs. And also is for using swarm mission. So we consider the multi-target reconnaissance assignments for continued missions after fault occur. So this is the process of our proposed task assignment algorithm. When it knows the current location of the UAVs and targets position, the targets are grouped by K-means algorithm, as you can see. And after that, the task assignment is performed using the Hungarian algorithm. And in this case, we consider the cost, the degree of failure. Okay, in this study, we need to using the very limited number UAV, then assign it, then the target many targets. So it is necessary to group the target number target. So we perform the target grouping by using the K-means algorithm. The K-means algorithm is a data partitioning algorithm which is assigned the observation n to previously one of the K cluster defines. So the K is chosen before the using the algorithms start algorithm. In this in this study, we set the number n is the total number of the target, and K is the number of UAV that capable of reconnaissance mission. Here's the or steps of the K-means algorithm. So as you can see, the number step 4. It computes the distance from each observation to each each centroid, and assign each observation to its closest centroid. So. And each is the K-means algorithm repeats at step 4 until K centroids are chosen. So after the target grouping is done, the task assignment algorithm is performed. We selected a task assignment algorithm, Hungarian algorithm for task assignment. It can be assigned the task by the 1-for-1 matching to identify the lowest cost solution. Here's the example of a procedure of Hungarian algorithm. At first, subtract the smallest cost in each row. And next, the same action. The smallest cost subtract its column. Yeah, and draw the line. Draw the row and column, and 0 are covered. A minimum number of such line is used. And repeat until the complete the four targets, as you can see. So this Hungarian algorithm for using the many cases, but is when the one-to-one matching cases are. I'm sorry. Many use these cases. This is a relevant research. What I motivated the research. The following papers were referred to establish the concept of this study. At this paper, using Hungarian algorithm for UAV station and UAV and station matchings. The left image is a concept of the UAV, their station matching, and right image is the set of the metrics interpretation of the Hungarian algorithm. They consider the cost using energy minimization and consider the distance. So in this research, we consider the fault severity and the distance for set the cost. It is divided into the following 3 stages according to the severity, and the cost calculation goes through the process, right on the right side. So we simulated we performed the simulated to compare the performance of the task assignment algorithm. It is assumed that the location and the number of targets are known in advance. And the fault severity of each UAVs is diagnosed as UAVs for diagnosis model. And for the performance analysis, simulated according to three variables, as you can see. We tried the case 1 and 2, 3. In simulation 1 case is a performance comparison according to the total number of targets. This green one is level 3 UAV, and blue one is level 2, and the red one is hazard for level 1 cases. The table below shows the average value of the result of 50 simulation according to the total number of target cases. More targets were assigned than, as you can see, the more targets, simply distance minimum was considered, and level 3 vehicles and level 2 vehicles were assigned close in all cases. And simulation 2 is considering the rate of fault to UAVs in swarm condition. In this case, there are much more level 3 UAVs or even more level 2 UAVs. The performance is so similar. The average search target is similar, as you can see. But the level 3 vehicle are assigned further target, and while the level 2 vehicles are assigned closure. And the case 3 simulation is considered the all targets assignment. It's a similar trend as case 1 and 2. The level 2 moving distance are shorter than other UAVs, and level 3s are more assigned. So our simulation is conclusion. Here's the simulation results show that the moving distance of the level 2 UAVs is shorter and more assigned to the level 3 than when only consider the minimum distance. This means that the movement required for the level 2 vehicles are short, and it uses less energy than level 3 cases. But in this simulation has some limitation because our assume is very simple. So if we want get a more realistic result, we need to consider energy minimization is more detailed. And I just divided only 3 cases, level 3 to 1. So it's more self-divided is required to consider the degree of fault. So in the future work, so we will link with the fault diagnosis model and using the fault diagnosis conclusion. So summary, my conclusions. We designed the Hungarian algorithm-based reconnaissance task assignments. And we target using K-means algorithm for the target grouping, and we consider the fault severity for set the cost. In the future, we, as I said, we consider the realistic factor such as a battery of UAV and energy level directory, and we will link with the actuator fault diagnosis model to more detail. And this is my flight test when using. It's a flight test. What I did. In the future, I will embodied our proposed algorithm to the task assignment, and we'll do a swim flight test. Thank you for attention. Do you have a question? Please give me the questions. Thank you.
All right, thank you very much, Tae-Gyun, for this presentation. Are there any questions from the audience? Yeah, here, or a question there? Yes?
What happens if there are more targets than drones available? So, is it dropping some targets then if it can't watch it all, or is there any consideration in this direction?
I'm sorry, please.
Quick summation of the question. What happens if the drones aren't capable to follow all targets?
For targets? When? I'm sorry.
Yeah, for example, if you go yeah, here you have all these targets, and somehow if the drones aren't able to minimize the distance to some of the targets,
Yep.
What happens? Will they just drop them, or will they still try to cover that target?
I understand that. Thank you for questions. In this case, we just search and only consider search and reconnaissance. So we only consider that go to the center of the targets. So it's a maybe limitation of our simulation. We just consider the moving to the center of the targets, and as you can see, such as after mission, so we didn't consider yet. So in the future we will consider such missions, other missions. Is this enough for? Is enough for explain? Thank you.
Is your question already answered, Guido? Not yet?
So thank you for the presentation.
Yep.
The Hungarian algorithm, does it run centrally, or can they do it in a distributed fashion? So is there one computer that calculates everything for all the drones, or do the drones calculate locally what they should do?
Thank you. Thank you. Thank you. Great question. We in the future maybe it's also in my case I just consider the one computer, and after the calculated result, the trans to the other UAV. It means just only I calculate only one computer. So in the future, I didn't consider the distributed computation. I just considered only reader calculation cases. Yeah.
I have maybe one final question.
Yep.
So I noticed you have 3 levels of failure, like a small failure, medium failure, and a hard failure.
A hard failure, yes.
How do you translate like something that happens during the flight into one of these failure levels, and then how do you use that to replan?
Okay. I'm sorry to explain about these conditions. The level 3, the minor fault is only considered a normal case and a very minor fault cases, such as actually a little fault. And the major fault is cases considered a low battery case, and one actually the partially fault. And in hazard case, a hazard fault case is a very low battery, so you need to come back to return to home. And one actual data is completely fault. So in this simulation, only consider these status. Yeah.
Thank you very much. If there's no more questions for Tae-Hyun, then I think we can thank him one more time.
Yeah. Thank you very much.
And then the next speaker can come on the stage. The next presentation is from Gauthier Hattenberger. Do I say it correctly, actually? Is it the French pronunciation? Hattenberger? No. The German one, okay. Hattenberger, then. All right, Gauthier is a long-time celebrity here at IMAV, so I think most of you will know Gauthier already. Well, I'll give you the floor. The mic is down here.
Okay, so thank you and sorry for this small delay. So today I'm going to present my work with my colleague Murat Brons and Jean-Philippe Condomine. We are all researchers at INAC, which is the French National Civil Aviation University. So estimating the wind with UAVs can be useful in many situations that can be used for a trajectory optimization purpose, but also for aerodynamic studies or atmospheric studies in general. And the common way to do that is to use either direct wind measurement or at least relative wind measurement like ultrasound or pressure sensor. And you can also extract this information from the trajectory itself. In a fixed wing, you can use the ground speed when you fly in circle, for instance. And with the quadcopter, or any multicopter style airframe, you can use the relation between the attitude and the drag. And this topic is actually following an article that we have presented last year at the IMAV 21. It was a virtual event, but we have set some basics on estimating the wind from a quadrotor. It was not the first time, but in this previous study, we had some limitations. So one of them is that we only have one configuration in terms of mass, shape, propellers, and stuff. And the other thing is that we were using quite complex procedure, using complex setups to extract the drag model. So for this new study, we would like to investigate the effect of the characteristic of the multicopter in terms of mass, shape. It should be also motors and propellers, but we couldn't do that yet, so we will concentrate on the effect of mass and shape on the drag and the estimation of wing. And the second thing is, can we extract this drag model, drag characteristic from an easier procedure from just real flights outdoor with specific calibration patterns and to make it available for anyone. So after introducing briefly the model, I will present again these two objectives in terms of effects of mass and shape and calibration procedure. So basically the model is based on two equations. The first one is known as the wind triangle. It says that the ground kinematic speed, Vk, is equal to the relative speed, Vr, plus the wind speed. And the second one is the Newton's law of motion, saying that the kinematic acceleration, so the derivative of the ground speed, is equal to the gravity plus the specific drag and the specific thrust. Finally, in the presence of wind, the orientation of the thrust is used to balance the drag and the own acceleration in the kinematic frame of the frame. Again, we need a model for the drag and the thrust. Usually the drag is something with a quadratic form of the speed, but from our previous studies, we have seen that at low speed, so it means below 10 meters per second, we have something which is closer to a linear relation between the drag and the speed. Again, we can only use this model at low speed. And for the thrust, we have this relation, assuming that the total thrust is in the body z-axis. We can project this total thrust into the Earth frame by using the rotation matrix here. So finally, if we don't have any vertical acceleration, we can tell that the weight is compensated by Tz, which is the projection of the total thrust on the vertical axis. So in your equation at the beginning, the Newton's law, we have, again, the gravity, the drag model, linear with the relative airspeed, and the specific thrust, which is only a relation, which is only dependent of the orientation of the quad, stating that the mass is, simplifying from the specific thrust and the mass here. The setup is the same that the previous study, but we have been able to arrange some variation. So from the initial frame with a mass of 550 grams, we have added some extra mass, so four small mass of 130 grams, and without changing the general shape. So we can assume that the drag coming from the shape is not changing, just the weight of the aircraft is changing. And we can also change the shape by putting this spherical body on top around the central part of the frame. And for the calibration, we are using the motion capture system, so in our case, the OptiTrack here. This is an indoor flight, controlled flight in front of a wind generator coming from the company WindShape. So with this complex setup, we are able to make automatic flight turning around the wind flow and extracting from the bank angle towards the wind the relation between drag and speed, and then extracting the drag coefficient. So we have tested a few configurations. Again, the 5 different mass from the base model and the 1, 2, 3, and 4 extra small mass, and the spherical body without extra mass at 9 different speeds from 2.5 to 12.5. And you can see in the results here, first the obvious effect of the wind. So when the wind gets stronger, the banking angle here, so on the left you have the bank angle, as a function of the wind speed. So when you have more wind, it's banking more and more. And also you have the effect of the mass. If you look at the color, when the mass is getting higher and higher, the bank angle is reducing for the same speed. The drag coefficient is extracted from these curves by computing more or less the slope of each of these curves. And if you put that in this graph, you can see that when the mass is increasing with the same shape, the linear drag coefficient is also increasing. And if you change the shape for a given mass here, well, increasing the size of the aircraft will also increase the drag, and that's something to be expected, of course. So let's analyze a bit. Again, first obvious thing, when the speed is increasing, the bank angle is increasing, and that's coming directly from the drag model, so no surprise. The second thing is that when the mass is increasing, the bank angle is decreasing. So you can see it with the colors here. This is really obvious. And the reason is that when at lower thrust, if you want to compensate the same drag, here, so the green is lightest, and if you want to generate the same force to compensate the same drag, you will need to bank more. But it doesn't mean that the drag is the same for a light and heavy plane, and this is something that we can see here. When the heavy plane, when the plane is getting heavier, the drag is also increasing, and we suspect that this is related to the rotation speed of the motors and something that is known as the H-force in the helicopter world. And this H-force is actually known to be linear with speed. So at low speed, this force is most likely the one that is getting this linear relation with speed. And at higher speed, the usual friction drag is getting dominance again. And finally, another obvious observation is that if you increase the body size, the drag coefficient will increase. However, we are not that much interested into the K only parameter. It's the K over M. If you recall the equations at the beginning, we have this ratio of drag over mass in the specific drag model. And if you look at this, so as a function of the mass, you can see that you can get higher ratio K over M for smaller drones, and even the heavy drone with the large body generating a lot of drag is just as equal as the small lightest configuration. So why are we so interested in this coefficient? Is because it's directly related to the observability of the wind. If this parameter is increasing, it means that you will have to bank more for a given wind speed, and your estimation of the wind directly related to this bank angle will get more accuracy. So if you want to optimize your frame to get a good estimation of the wind, you have to look for some light frames generating high drag and most likely with high RPM, which is the exact opposite of what you would do for another mission like a package delivery, where you are looking for the heaviest payload possible with the lowest drag and the lowest RPM to get low energy consumption. So yeah, optimizing something is really related to your mission. For my second part, can we get rid of all this nice OptiTrack and WindShape device to get the estimation of the drag coefficient? So the idea is, if we assume that we can fly outdoor at a constant wind speed, and if we can make a good square trajectory at a constant altitude, we will be able to see the wind from any direction, and we can subtract that and get some information about the banking in all the different legs. And finally, we are going to use a least square algorithm to minimize the residual of this objective function, where the unknown parameters are the K/M ratio, the winds from the X and Y direction, and the residual is, well, it's built from the Newton's law, again, with the kinematic acceleration, the gravity oriented with the orientation of the quad, the K/M parameter that we are looking for, and the relative speed, which is computed as the difference between the kinematic speed coming from the GPS and the wind speed that we are trying to estimate. So if you run this procedure in simulation with different simulated winds and using the perfect simulated data from the flight model, you can see that this is working very well, and the fixed K/M ratio that you have set in the simulation is correctly estimated, as well as the wind speed also set in the simulation, at least very close to that. Now let's try the same thing outdoor, and we have tested 3 configurations. So the first one is the light frame, so no extra mass. The second one is the basic frame but with some extra mass, and the last version is the frame with this spherical body around it. This is exactly the same procedure, and you can recognize the Murray airfield close to Toulouse. We are taking off from here and making this square trajectory, and then we are just extracting the relevant part of the trajectory and applying this optimization algorithm to extract the coefficient, and there you can see that it's really wrong. Even the wind is pretty off, so according to the public weather data, the wind should have been between 2.5 and 3 meters per second, but with a lot of gust. And from the ground, it was not that obvious, by the way. The estimated wind is somehow quite strong, correct direction, but strong. And the estimated coefficients here are very far from the real values that we have computed during the calibration. And I don't think we can really use that at the moment. So that's quite obvious that it cannot be as good in real life as in simulation. That's something that we know. But can we explain why we are so wrong? The first assumption that the wind is constant is probably something which is not realistic enough. It's very hard to make a long leg so we get a proper trajectory at a constant bank angle during the calibration flight and still get the square done in a very short period of time. So it's not changing a lot in terms of wind condition. Here the solution would be to fly on a very calm day, early in the morning maybe, or, well, something else. The present data set that we have is not good enough in that regard. Every flight that we have, the wind was too gusty to extract anything. So we have to do that again. And the other thing is, if you look at the graphs here, so the dotted lines, dashed lines here are the error between the acceleration in blue and the specific thrust plus drag, so all those specific forces, and they should match, because the idea is to reduce this error to 0 at all points by the least square algorithm. And you can see that during the acceleration phases, so when it's changing direction, this is going very wrong between the these two lines. Maybe it's coming from the post-filtering. It's smoothing a bit too much the data. One option would be to just extract all those parts from the data set and only consider the parts where the acceleration is really constant. So, as a conclusion, I would say that the characteristics that are affecting the drag of an aircraft are, well, if you want to design an aircraft to observe the winds, your optimal design will be probably very far from what you expect from many other missions. So you have many small elements that should be taken into consideration to get a proper estimation of the wind. And for the second part, where the calibration procedure using outdoor flights, again, it's possible in theory to do that, but we need to get a better data set and to define properly the good condition to extract correctly the coefficients and to make it work in practice. And it's not very, well, we are not yet at that point. So some of the future works that we are planning in on that matter are introducing a Kalman filter for the onboard estimation of the drag. So we do have a Kalman filter to estimate the wind with known parameters, but if you add the unknown parameters of the drag model into the Kalman filter, you have some low observability issue that we have to solve. We can also investigate the effect of the drone size and propeller size just to be sure that this H-drag model is valid. And finally, we would like to integrate the wind estimation from several drones into a dense map to get the surrounding wind field in large places like cities or anything else. Thank you.
For this presentation. Are there any questions from the audience?
I have a question about the flying height, the influence of flying height. One is wind shear, say the difference in wind speed with height, and the other aspect could be the ground effect of a quadrotor flying above ground. Two effects which could be influencing your measurements. Can you say something about that?
So the flying altitude that we have tested were between 15 for the lowest to, I would say, 40 for the highest altitude. Of course, we have tried to go at higher position to get rid of the ground effects, but that didn't help much, and most likely the intensity of the wind and the disturbance were not so lower at higher altitude. Again, it doesn't matter about the intensity of the wind, but more, is it regular or not? So at low altitude, I mean below 100 meters, for now we cannot tell this is better working at 10, 50, or 100. We don't see a huge difference at the moment. And higher, we don't know. We are not allowed to fly.
The question here.
Thanks for the speech. A very interesting problem. I have a couple of comments more than questions, but you can then make your thoughts on my comments. Are you aware of the work by Theodor Tomic, DLR, his PhD thesis, there are a couple of works in which he tries to use the quadrotor as a wind sensor also. I wonder.
Well, I have, of course, we have read a couple of articles regarding that. Most of the other works are, not all, but most of them are considering the modeling of the thrust, which is probably one of the biggest errors that we are committing on the estimation of thrust, is that we only rely on the bank angle and the fact that we know the mass. And other people are using the RPM of the model of the motors and try to estimate or to model the thrust. We would like to avoid this part, especially because you need again a complex setup to get a proper estimation of your thrust model. So yeah, we are aware of different practices like this, and we want to avoid this modeling of the thrust.
I see it clearly. And regarding so your method is assuming some static relation, right? You really try to have acceleration zero, I guess. Zero acceleration, and then to fit.
During the calibration parts in front of the wind shape, yes.
Yeah.
For the second part, we were expecting that we can take into account the acceleration computed directly from the kinematic speed, the derivative of the kinematic speed.
But you assume
but
that
obviously this is where it gets the wrong part.
But for example, you assume that the wind is constant. Yeah.
Yes.
Would it be possible to instead consider a dynamic changing wind and then try to reconstruct the history of wind? And also considering this dynamicity, instead of considering always a constant banking angle, what if you try to generalize the method to a time-varying banking angle, considering the full equations and the full estimation?
In this case here, we feed the algorithm with the known parameters are actually the banking angles and the ground speed. So we feed ground speed and banking angle. We compute the acceleration from the derivative of the ground speed, and from that we try to fit the model of constant wind and constant drag coefficient. And this is where it's not working as expected. It can be from wrong estimation of the acceleration, wrong estimation of the thrust, and again, one option would be to get a better trajectory, eliminates the part where we are wrongly estimating the acceleration, so the turns and things like that. And again, the dataset is not good enough, in my opinion. I don't know if a good dataset will be enough, but...
Okay, thanks.
All right, I think this is a very nice discussion, but we have to go to lunch, actually. And the lunch is served in the foyer. Oh, one thing I forgot. Let's thank Gauthier for his presentation again. So the lunch is served in the same place where we had the coffee, and we continue here at 1:30. So please be back here at 1:30. Thank you all.
Still together, we are one. So much time wasted playing games with love. So many tears have cried, so much pain inside. And baby, it ain't over till it's over. So many years we've tried to keep our love alive, but baby, it ain't over till it's over. times did we give up? But we always work things out. And all my doubts and fear kept me wondering if we always be in love. So many tears have cried, so much pain inside. But baby, it ain't over till it's over. So many years we've tried to keep our love alive. But baby, it ain't over till it's over.
I come awake with the gift for womankind. You're still asleep, but the gift don't seem to mind. Rise on this occasion, halfway up your back, sliding down your body, touching your behind. You look so self-possessed. I won't disturb your rest. It's lovely when you're sleeping, but wide awake is best. Wake up and make love with me. Wake up and make love. Wake up and make love with me. I don't wanna make you, I let the fancy take you, and you wake up and make love. You come awake in a horny morning mood, and we have a proper wriggle in the naughty naked nude. Roll against my body, get me where you want me. What happens next is private, it's also very rude. I go and get the post and make some tea and toast. You have another sleep, love. It's me that needs it most. Wake up and make love with me. Wake up and make love. Wake up and make love with me. I don't wanna make you, I let the fancy take you, and you wake up and make love. Wake up and make love with me. Wake up and make love. Wake up and make love with me. I don't wanna make you, I let the fancy take you, and you wake up and make love.
To love us by us, caress us, stand by us. To love us, stand by us, caress us, stand by us. Let's move it on up. Stand by us. seemed so far away. Now it looks as though they're here to stay. Oh, I believe in yesterday. Suddenly, I'm not half the one I used to be. There's a shadow hanging over me. Oh, yesterday came suddenly. Why he had to go, I don't know. He wouldn't say. I said something wrong. Now I long for yesterday. Yesterday, love was such an easy game to play. Now I need a place to hide away. Oh, I believe in yesterday. Why he had to go, I don't know. He wouldn't say. I said something wrong. Now I long for yesterday. Yesterday, love was such an easy game to play. Now I need a place to hide away. Oh, I believe in yesterday. Oh, I believe in yesterday.
Expectations make no sense when every answer's wrong. You're fighting with lost confidence, all expectations gone. The time has come to make or break. Move on, don't hesitate. Break out, don't stop to ask. Now you've found a break to make it last. You've got to find a way. So what you want to say, break out. When situations never change, tomorrow looks unsure. Don't leave your destiny to chance. What are you waiting for? The time has come to make or break. Break out. Don't stop to ask. Now you've found a break to make it last. You've got to find a way. Say what you want to say. Break out. Break out. Don't stop to ask. Now you found a break to make it last. You've got to find a way. So what you want to say, break out and round. Don't stop to ask. Now you found a break to make it last. You've got to find a way. Say what you want to say,
down. You got it thought. I've seen the thuggers around, and I know, baby, just how you feel. You got to roll with the punches to get to what's real. Oh, can't you see me standing here? I've got my back against the record machine. I ain't the worst that you've seen. Oh, can't you see what I mean? Might as well jump. Might as well jump. Go ahead, jump. Go ahead, jump. Hey, you, who said that? Baby, how you been? Say you don't know, you won't know until you begin. Well, can't you see me standing here? I've got my back against the record machine. I ain't the worst that you've seen. Oh, can't you see what I mean? Might as well jump. Go ahead, jump. Might as well jump. Go ahead, jump. Woo-hoo. Might as well jump, jump, go ahead, jump. Might as well jump, woo. Go ahead, jump, jump, jump. You might as well jump, yeah. Go ahead, jump. Might as well jump. I said go ahead, jump, jump. Woo-hoo.
When I find myself in times of trouble, Mother Mary comes to me, speaking words of wisdom, let it be. And in my hour of darkness, she is standing right in front of me, speaking words of wisdom, let it be. Let it be, let it be, let it be, let it be. Whisper words of wisdom, let it be. And when the broken-hearted people living in the world agree, there will be an answer, let it be. For though they may be parted, there is still a chance that they will see. There will be an answer, let it be. Let it be, let it be, let it be, let it be. There will be an answer, let it be. is still a light that shines with me. Shine until tomorrow, let it be. I wake up to the sound of music. Mother Mary comes to me, speaking words of wisdom. Let it be, let it be, let it be, let it be, let it be. There will be an answer, let it be.
Today is gonna be the day that you're gonna throw it back to you. By now you should have somehow realized what you gotta do. I don't believe that anybody feels the way I do about you now. Baby, the word is on the street that the fire in your heart is out. I'm sure you had it all before, but you never really had a doubt. I don't believe that anybody feels the way I do about you now. And all the roads we have to walk are winding, and all the lights that lead us, they are blinding.
Sometimes I feel I've got you. Run away, I've got you. Get away from the pain you drive into the heart of me. The love we share seems to go nowhere, and I've lost my light. For a twist and turn, I can't sleep at night. Once I ran to you, now I run from you. This tainted love you've given, I give you all a boy could give you. Take my tears and that's not nearly all. Tainted love, tainted love. Now I know I've got you. Run away, I've got you. Get away. You don't really want any more from me. To make things right, you need someone to hold you tight. And you think love is to pray, but I'm sorry, I don't pray that way. Once I ran to you, now I run from you. This tainted love you've given, I give you all a boy could give you. Take my tears and that's not nearly all. Tainted love, tainted love. Don't touch me, please, I cannot stand the way you tease. I love you, though you hurt me so. Now I'm going to pack my things and go. Once I ran to you, now I run from you. This tainted love you've given, I give you all a boy could give you. Take my tears, and that's not nearly all. Tainted love.
Here come a flat up, he come, grooving up slowly, he got juju eyeball, he won't holy folder, he got hair down to his knee. Got to be a joker, he just do what he please. He wear no shoes and he got Trojan football, he got monkey finger, he shoot Coca-Cola, he say, I know you, you know me. One thing I can tell you is you got to be free. Come together right now over me. He back protection, he got walrus gambut, he got on a sideboard, he won't spine a cracker, he got feet down below his knee. Hold you in his armchair, you can feel his disease. Come together right now over me. so how does she come together right now of me? The deal, the deal, the deal, deal, don't be, over me. Working on the weekend, baby. She's working all through the night and jump into the deep end, gave her the evidence she required. Take 5, she's got pearls. Don't fake it when it comes to making money, so she smiles, but that's cruel. If you knew what you think, if you knew what she was after. Sometimes she wonders and she laughs in her frustration. Would someone please explain the reason for this strange behavior in exploitation's name? We must be working for the skin trade. Doctors of the revolution gave us the medicine we desire.
Okay. Hello? Okay, so let's still give it a few minutes for people to enter. Perhaps it's possible to see the screen of the keynote speaker, then we know, perfect. And so while people are walking in, welcome back. That was quite a quick lunch. And so the reason that Dutch people eat sandwiches for lunch is because it's so quick. And so now you know why. Actually, on other days we may sometimes also have a warm lunch for you, so that's also nice. Yeah, so I'm very honored today that we have really also a research star amongst us, Antonio Franchi. And so he's a full professor in aerial robotics at the University of Twente. Twente is a city in the east of the Netherlands. It's really quite a nice region. So Antonio did his master's and PhD at Sapienza University in the most beautiful city in the world, Rome, obviously. And he also was a researcher at the Max Planck Institute, also University of Santa Barbara in California. And he's also still associated with the LAS CNRS in France. And his main expertise is on estimation and control, for things also like interaction, drones that interact with objects, but also multiple drones. And I think that the title of today's talk is very interesting, so I'm very curious what you're going to say. So without further ado, Antonio, the floor is yours.
Thanks. Can you hear me? Yeah. Thanks, Guido, for the introduction and all the organization panel for the invitation. It's really a true honor to be here with you today. So let me start by let's say best way to move from a point to another if these 2 points are very far in space. And so since the mythology, the Greek mythology, So I see here the Prometheus example at TU Delft. I learned today that it refers to this mythology. There is another myth that is the myth of Daedalus, which is also very related to this. And passing through the attempts of many engineers and scientists like Leonardo da Vinci or pioneers of flight who tried to fly in many different ways until the Wright brothers, we finally managed to achieve these very long distances in relatively short time dream. Now we can, with modern aviation, fly everywhere in the world and even outside of our atmosphere. So instead, another problem which also started in maneuverability and mechanical simplicity is I'm talking about the Sikorsky R4 hoverfly. Okay, so then for decades, we saw the predominance of helicopters, and there was then there were in the 70s and or even 60s, 70s some designs that were a bit unorthodox, but we never got back really to designs that were like the one in the early stage. Until roboticists started to have some wish to go in the 3D world. And this, so I refer to this period, this is a more or less 10 years period from basically the 2000 decade, that I call it the decade of the pioneers. So around in 1990s period, the roboticists had somehow mastered the control and the control of robots and design of robots that had to move on the ground. So mobile robotics was a well-explored subject in 2D. And roboticists wanted to extend to 3D their research domain. So they already developed many platforms on 2D, which, by the way, this posed the ground for the development then about autonomous cars, for example. This dates back to that age. So roboticists wanted to go to the 3D. And so the first thing you have to decide is which platform are we going to use in order to deal with this with the robotics problems in 3D. And then I did my research, and I saw that actually, very related to this conference, to this event, the first aerial robotics conference competition was in 1992, organized in the US. It was the International Aerial Robotics Competition, and the goal of the competition was to move a metallic disc from one side of an arena to another side. So to grab this disc and to move it somewhere else. This was 1991, completely autonomously. So you had to have a flying system that autonomously had to pick up this object and move it there without any human intervention. This competition lasted 2 or 3 years. I mean, I think the winner was even 4 years after the competition was launched. There was one team that finally made it. And there were many different designs used. This is an example of 3 designs that were used at that time. One is a tail-seater on the left. One is a blimp, and another is an helicopter, a small-scale helicopter, and by the Stanford team, who actually won finally, made the task. So those platforms, all of them were actually not suitable for roboticists at that time. Why? Because they were dangerous, they were polluting, of course, they were expensive to build and to maintain. This robotics lab didn't have an unlimited amount of money to build their platforms. They were optimized to covering mainly distances, but not very precise in positioning. And what roboticists typically want is to precisely position their end effector, let's say, or generalized end effector somewhere. They just don't want just to transport or to move roughly from one point to another. Not suitable for indoor, and the labs wanted to stay indoor, to do their research indoor, of course. They were either too big or not. Definitely, you don't want to use something like this, something like the helicopter, for example, indoor. And also, but very importantly, they were hard to control, either because of external disturbance. For example, the blimp, in the video I've shown you before, the blimp after 1 minute just is flown away by the wind, and there is a pure student who is running after the blimp. Or because of actuation coupling. So for the tail seater and the helicopter suffer by this problem. And I want to spend a couple of slides on this. So if you want to laterally control the motion of an helicopter or a tail seater, these are, since they are under-actuated, you need to move to do a pitching, okay? In order that, so that the thrust, we have seen it in the last talk today, for example, but we see it every day. You see this every day. In order to have a projection of the thrust that is non-zero on the horizontal plane, so that it will accelerate in the horizontal plane. And this is not a problem in general. This is normal. You see this being done. Okay. So how this is generated? This pitch motion is generated on a helicopter. On a helicopter, apart from simplifying, I mean, apart from all the many other effects, the idea is that this wash plate slightly changes the direction of the thrust by a slight amount, but by changing the direction of the thrust, there is a pitching moment that is created because the thrust application line is not anymore passing through the center of mass. So the rigid body, that is the fuselage, tends to turn. Now, you have, in addition to this, also the fact that the thrust, since changed its direction, has also a non-zero projection on the horizontal plane already before that the whole body tilts. So it's a kind of anticipating what you would like to do. Okay, so this means that there is a coupling between the tilting and the motion, the forward motion. So the dynamics, the translational dynamics. Because of this, you have what is called a non-zero, non-asymptotically stable zero dynamics. In this case, you have basically, when you linearize the system, you see this complex conjugate pure imaginary poles. For the tail seater, it's even worse because you have the center of mass above. So if you want to tilt the tail seater in a certain direction, like this one, you want to tilt it like this. We look at the screen. You need to have a force, thrust that changes slightly on the opposite direction, but through the flaps. Okay, so you have your desired pitching moment, but what you get is also a force that goes backward. So what you will see in this system is that if you want to go forward, you will first start to go backward, and then you will go forward. And this is a zero dynamics that is even unstable. This doesn't mean that those systems are not controllable. They can be controlled. They can move and they can be stabilized, let's say. But it means that basically, as has been shown in a paper, a seminal paper in '98 by Cohen and Sastry, the fact that you have this term here, that can you see my? No, maybe here. The fact that you have this term here that couples the actuation of the orientational dynamics with the translational dynamics makes the system makes the fact that you cannot track exactly a certain trajectory in position. You can only track it in an approximate way. If you would like to zero the error tracking a certain trajectory, you will have an unstable or zero dynamics. So the system will track theoretically the trajectory, but there will be a part of the remaining state that will just go crazy or oscillate and have some undesired behavior. But if we neglect those forces, which are called the small body forces, and we consider another model, that is the one below, actually this system, this model here, doesn't have a zero dynamics.
And so it is also called differentially flat or dynamically feedback linearizable. However, this system is not exactly like the one of an helicopter, but you can still use it to control the helicopter. You won't have a perfect tracking, but you don't have instability. But you don't have perfect tracking, so it's not good for roboticists. Okay, because if I want to grab something somewhere, because I want to do, robotics is about physical interaction, and if I cannot control precisely the position of my end effector, what can I do with this system as a roboticist? Okay, in the 90s, at the same time, more or less the same time, there were those first toys that were RC controlled, like the gyro saucer was called, this one in Japan. It could be remotely controlled, okay? So this is not automatically controlled. And this is an advertisement from that age. And also there were some companies that were selling this Dragon, one for example selling the Dragon Flyer quadrotor, one of the first quadrotor, again remotely controlled. So those platforms, which were different from the one we have seen before, they were actually good platform, promising platform for aerial robotics. Why? Because they were small and electric, so you could use them indoor. For example, they were cheap, very cheap components to be built, and also robust, no strange or difficult mechanics. And they were promising in terms of positioning precision. In fact, if you write down the model of this system, you don't have anymore these small body forces, but not because you neglect them, but just because they don't appear at all. And to let you quickly understand why, to see the difference between the other system and this one, so in order to move laterally with a quadrotor, and so to create this pitch, so you still have an underactuated system, so you have to pitch in order to move forward. But now the pitching is not generated by changing the direction of the thrust in body frame, but just by changing, having a difference between the two thrusts of opposing rotors. This doesn't change the overall direction of the total thrust, it's still there. So this means that we have our pitching desired pitching moment, but we don't have any spurious force that is generated by this action. So the two actuation, let's say, levels are completely decoupled. So you don't have this nested zero dynamics or internal dynamics. And so from 2002, so the robotics understood that this was a very good platform possibly to be used, but they wanted to control the platform autonomously, not through RCs. So they started to, from one side, they started to attempt to build the platform from scratch, because the ones at the beginning starting to adapt the Dragon Flyer, for example, platform that we have seen before, and these are some attempts, and you cannot afford to destroy many of your prototypes. Finally, after many attempts and work, more or less around 2005, 6, 7, several labs started to have the first successful flights, automatically controlled flights of quadrotors, like CNRS or people like TPFL in Switzerland, Stanford in Australia. And one interesting thing as well that happened is that many of these attempts were successful, but actually using wrong assumptions. One example, and I really encourage, I see many young people here, I'm really happy, because I really encourage you to read this paper from 2010, which is called The True Role of Accelerometer Feedback in Quadrotor Control. This is a perfect story where you see basically that a model that works does not necessarily help you understanding a phenomenon. It might work in reality, but actually it might corroborate strong assumptions. And in this case in particular, the authors showed that the accelerometer on a quadrotor cannot be used as an inclinometer to understand the attitude, but what actually measures is the speed, thanks to the rotor drag. And so when people use attitude controllers that thinking to use it as the accelerometer as an attitude sensor. What they are actually doing is something wrong. It's like if they are using a velocity controller but instead it's a position controller, and so they are feeding the wrong measurement in the system. So the question is then, how can this work? You are using the wrong sensor, okay? And the reason why it works is because actually, if you write down then what happens is that the controlled system is stable even if this measurement is fed in the wrong way. And what you're doing when you control the attitude with an accelerometer is that you are actually controlling the speed, stabilizing the speed, not the attitude. So it's a very, very interesting lesson learned from this development. Finally, at the end of this decade, the control of quadrotor was fully mastered. So we saw aerobatic flights in 2010, 2011 by several labs in the world. These are just two examples at UPenn and TTH. However, they were using perfect state estimation, so motion capture. So they stepped away from vision in order to do this. They were indoors, so there was no wind, no external disturbances. The environment was static, known, and well structured. But this was, I would say, for me, this represented the end of a decade. And then, thanks to the influence from other industries like consumer industry, a smartphone, or movie industry, we started to see commercially available quadrotor that could be used for research, even in labs and that were not expert on drones, but they could use it just as a robotics platform, finally. So this is basically more than 10 years after robotics wanted to go in 3D. So I did a small search about this decade, and I searched for the number of publications on IEEE Explore that have one of those words, so quadrotor, quadcopter, quadcopter, etc. And this is the number of publications that you see. And actually, if we look with my chronology, so in '99 you have this, 98, this paper, seminal paper by Cohen Saxtree, where actually the model of a quadrotor that then is used was written there. Everything is there. And also the fact that it can be controlled, is feedback linearizable, is differentially flat, it's there already. But then there was this part at the beginning, which there were early theoretical papers, and they tried to start to build the platform. And mastering of automatic hovering stabilization is done here. And in this part, as I said, there were many theoretical works using much more complex models and a lot of research, let's say, time wasted in some way. And finally, at the end, we have the mastering of the automatic control. So then after this decade is over, this pioneering decade is over, one might think, okay, now the quadrotor control problem is solved. You know? What is left for the next 10 years? If we look for control of this platform, there should be no much work anymore. So what do you expect the numbers in the next decade will look like? Who thinks they will, let's say the numbers will stay constant, like the last? Who thinks they will double, or triplicate, 4 times, 5 times, 10 times? Okay, these are the numbers. So yes, basically almost 10 times. So well, then one can ask, what happened here? This is what I call the golden age, because thanks to the work done in these 10 years, then the platform is available and people started really, in research, in robotics research, started to use it. Into times or going to different configurations, taking into account failures, for example, or doing aerial physical interaction and manipulation. And by the way, physical interaction was the first objective of the first robotics challenge in '91, where they had to pick the object, so to physically interact with the world and move it. And actually, I belong as a researcher to this age. I grew up in this age, because in 2010 I started my postdoc in the Max Planck. Before that, I didn't work on flying vehicles, and then I was a bit in the transition phase. I saw the first work by UPenn and ETH. I saw it starting, but my background was not on multi-rotor. So I had to quickly, let's say, catch up in 1 year, all the 10 years that people did before I started. I lived on in my experience this, so having to learn how to code low level, how to build and to make and have many crashes and to customize and so on. At that time there was not a single platform, and then I started immediately to use this platform as a roboticist that is not interested in particular in flight, but more as to them as 3D robots, and to use them, for example, for multi-robot coordination or for human-robot teleoperation, for example. In the second phase, instead, at a certain moment, I started to be more interested in really new multi-rotor designs and aerial physical interaction and manipulation. So really, I got fascinated by the subject by itself, not anymore by aerial platforms as tools. And so my path in this decade can be an example of a path of somebody like other people in the field that lived this decade. So I would like to recap some of the things we did together with my collaborators and my students in this time, in this period. But just as an example of what happened in this golden age. And so I'm just a small sample of the super exciting things that we were able to do as a community in this period, starting from, remember, these early flights of the first quadrotors. So one thing we did, for example, was a bilateral control of many 3D robots, where bilateral means to have force feedback with human in the loop. We even did an intercontinental teleoperation from Germany to Korea with haptic feedback, and there the problem is, for example, on maintaining stability despite the delays, for example. Then another thing we worked on is to go beyond standard quadrotors and collinear platforms and consider designs that have tilted rotors in order to obtain full 6D control of the platform. So full actuation, omnidirectionality, and 6D tracking, and even manipulation. As you have seen in my previous example, this differential flatness property is very important in order to achieve perfect tracking. And I worked on several different cases in which my goal was really to see whether the system could be modeled with a differentially flat system, so that precise control could be done. For example, we discovered that tethered aerial vehicles like this one are differentially flat, and the flat outputs are actually the angle and the cable tension. In this way, we could show, for example, landing on a sloped surface in a very smooth and relaxed way, because we could control the cable tension always to be positive, and we could control the angle for any possible trajectory. So you are not anymore subject to the under actuation. But these outputs can be controlled as you want, with any trajectory you want, while the rest of the state remains stable. Or we have shown that there are special classes of aerial manipulators. So aerial manipulators are platforms that have an arm and a flying base combined together. And there are special classes of these manipulators that we call the protocentric, that are differentially flat. And so this allows to have a very precise tracking, which is very important in aerial manipulation. We have shown that not only the model of Coe and Sastry is differentially flat, as they shown in '98, but even if you add the rotor drag, which appears and is very important in the case of very fast flight, even in that case, the system is differentially flat. And so that allowed a much more precise tracking at higher speed. We worked on fail-safe control and understanding when multi-rotors in general can still fly and be in hovering, not just in a, let's say, in a state in which they are perhaps spinning, but really being in static hovering when they lose one or more propellers, and how this is related to several geometrical properties of the allocation matrix, and which then in turn depends on the geometry of the system. So this is very helpful in order to design the platforms. We did physical interaction control with the manipulators using direct or indirect force measurements, and also motion planning. And this, for example, on the left here you see an example of a sensor that can estimate the depth of the metal, and so also where there are some defects. And this can be used in inspection and maintenance of large infrastructures. And the idea here is to avoid that people had to climb and risk their life in order to measure, to take this measurement. That require physical interaction. They cannot just be done with vision. And recently we also started to work on more complex problems that can be tackled only using optimization and predictive control, in order to tackle several, or to keep valid several constraints that you might have coming from perception or actuation. So the next decade. So today we can see, I mean, if we look around, if you go at ICRA or other robotics conferences, or of course also here at IMAV, you see that things still are moving. So you see, for example, multi-body, multi-rotors, okay, that have to be controlled. New designs that are capable of more complex maneuvers, but you still need to develop controllers for them. Or control of multiple UAVs together for manipulation. We have seen we are seeing vision-based and learning-based control for very fast maneuvers in the wild. Human-robot physical interaction with a flying robot, and also coordination, multi-robot coordination in physical interaction. And the example is large. You can see it's a very active field. So, but okay, this is now, but I would like to look forward. So what is next for control in aerial robotics? Before I start trying to answer this question, I think we need to understand what is actually automatic control for robotics. So in my view, this is my personal view, automatic control for robots, I see it basically as something that when you have a newly born robotic platform, takes this platform and makes this platform take the first breath, or the first steps. Because it allows it to really do the first basic things that on top of which everything else can build up. So in this way, I feel really fortunate to work in this field, to look at the robotics from this point of view, because I feel like a parent that helps the child to make the first steps. It's something that then becomes transparent. Like the fact that you walk, you don't think anymore about that, the fact that you're controlling your walking. So it becomes this transparent backbone of the autonomy. Because it ensures that you have reliable motion, and your motion is reliable, you are not falling every 10 steps, but also you have the required performance. You can also place your feet where you want while you are stepping, with the required performance, with the required precision that you need in order to do the task that you want on top of it. But of course, automatic control is not full autonomy. Automatic doesn't mean autonomy, because you also need the hardware design, perception, planning, reasoning, and these things are intertwined, by the way, as we have seen in the plenary of this morning, clearly. So how do you find, if you are a control robotics is in control, how do you find new research challenges? Given what I just said, what is automatic control for robotics, you find, I think, challenges in two main cases. If you have new hardware, when new hardware is available, but new hardware can be anything, can be new actuators, new sensors, new materials, new mechatronic designs, or new computation capabilities. This is all, all new hardware, let's say. So because when you have new hardware, you need new equation of motion, of actuation, or measurement. In the end, you need new models. And if you have new computational capabilities, you might try to apply, for example, control algorithms that were too heavy without that computation capabilities, and try to push forward the capability. So either you have new hardware, or you have a new motion tasks for the same hardware. You remember this helicopter, the slide of the helicopter, the Sirkowski one, so the one who finally won the competition for the best, let's say, vertical takeoff and landing platform. On the right, there was a pilot using a helicopter to do aerobatic maneuvers and flipping the helicopter, doing all crazy stuff, which was not intended at all at the beginning when people designed the first helicopter. So you can still have the same hardware, but change your wishes and say, oh, now with this hardware, I want to do new things. So I have new motion tasks. How can I can achieve this? Then control comes into play. So, or you want to have better accuracy, more faster, reject maybe different type of wind. So, but those things, having new hardware, motion task, and then developing new controller, they really go hand in hand. And actually, the evolution of control research is shaped by these changes, but at the same time shapes these changes, because if we have seen if a new hardware, many new hardware possibilities are created, then depending on how successful maybe it's to control these platforms, some of them are selected as the preliminary winners, and then maybe are then influence their evolution in terms of hardware development is influenced by what we are able as control engineers to do on this platform. So it's not something completely separated, of course, at all. So yes, new motion task may be triggered by the fact that you have new hardware, and also new hardware might be added if you need new motion tasks. In terms of new hardware, there is plenty. There is plenty of hardware that is over there that is still to be fully exploited, fully understood and used. There are many labs that try to propose, and there are sometimes hardwares, if you look in the literature, that were proposed and they appear only in one paper, and then you don't hear from them. But maybe that will be the design in the next decade. So my suggestion would be, don't underestimate, don't follow, if you want to make the difference in the future in research of control for aerial robotics, go back, learn, and look at this maybe possibly temporarily abandoned ideas. Because like the Botesat flying octopus, they might come back 80 years after. Okay. And then we also have when we consider, for example, physical interaction and manipulation, we have huge tons of hardware that still needs to be controlled in the proper way. Also, in terms of new sensors, there are many new sensors that appear every time. Don't stick with the particular sensor that is mainstream. This is my suggestion as well. look at the possible sensor. Of course, neuromorphic event cameras. We have seen an explosion in the recent years, as mentioned in the and dealt with in the first keynote of today. But for example, there are aerodynamic force sensing that start to come out, or this idea of using whiskers for fluid, to estimate the fluid velocity or pre-contact with the surface, and many other, or maybe you want to use estimate the wind using some technique, some method. Maybe the sensor is not just the sensor, but a method like we have seen this morning, a new method that uses the same hardware. So keep your eyes open if there is any possibility to measure something different than what you can measure now. New computation capabilities, of course, and then this might trigger machine learning or predictive control. And of course, new actuators and other than the typical quadrotor ones. For example, I think a very important one are the flapping wings, so that we have seen here. We see an example here with the Flapper Drones company, for example, Delft. I think that this is not yet fully exploited by roboticists. So flapping wing potential is not fully exploited. The models are not fully understood yet. There are some of these projects that are mentioned here in this slide. They try to do better modeling, and even maybe considering more hybrid approaches or morphable approach could be the future. In terms of new motion tasks, the list is very long. So aerial manipulation, transportation, inspection, flying actually and very fast. But in my view, the most challenging is something that nature is able now to achieve, but roboticists, aerial robotics is still very far from it. And it's an example is given by this bird, for example, and many other birds have this ability. They have this ability of stabilizing one part of their body incredibly with a very precise accuracy, while facing completely, let's say, unpredictable wind gusts, and using structure, maybe exploiting their partially soft design, let's say, natural design, maybe exploiting other things that are not at all understood by engineers at date. So I think that will be an extremely interesting challenge for control and design and all these disciplines that are connected to control in the future. And with this, I want to conclude by also acknowledge the many the many institutes that funded my research in the past, but most of all, I want to really say thanks to the many people who collaborated with me in the last years, and that made this incredibly inspiring and fulfilling journey possible. And I'm only looking forward for the next 10 years. Maybe some among you will be the one who will make the difference, like the pioneers of the quadrotor and the aerial robotics research. Thanks for the attention.
Thanks for the inspiring talk. Are there questions from the audience? Perhaps while you reflect a bit on it, a question to you. So you study these systems physically, so getting to new insights as well with like all these different configurations. In the same time, I see on your one of your last slides like deep learning, like end to end. Can you comment on that? Because basically, people in AI they kind of hope like. Okay, you give me some platform and I have an AI algorithm and it will just learn, and then I don't need to understand the physics, basically. I mean, that's freely said. So what is your opinion on this?
Yeah, that's a tough question. I think it's a psychological question. It boils down to psychology in the end. How much are you satisfied by the outcome of your research? So I can see that there could be some people who are satisfied enough by making the system just work, as I said, but something that works doesn't let you by, let's say, that is not, doesn't give you understanding, maybe. It doesn't, so it somehow psychologically might not satisfy you. And I think there are still, as long as there will be people that are not satisfied with the things that just work, but they really want to go beyond trying to understand better the world around us, there will be both approaches. But of course, okay, these are.
I know it's a bit provocative.
Yeah. But then, in terms of really, from an application point of view, or from a, let's say, more practical point of view, I think the two things are not in opposition. We have seen examples in robotics control and other fields, for example, in which learning can be used in order to deal with part of the system that are too complex to control, and to maybe steer the design to the most promising, the design and the control to the most promising directions. But then I think the work is not done there. We should not stop there. You should then ask yourself, okay, why this design that came up from learning is the best? Why? Or why this controller, why this way of controlling the robot works? So it should be the starting point to me, not the end point, if you are a researcher.
Yeah. Thank you. I couldn't agree more. Like when you do machine learning, to also study what the learning found, right? I mean, to analyze what the solution contains.
Exactly.
Thank you for that answer. Are there other questions in the audience? Yeah. Can I throw it to you, Pasquale? Can you try this? We're on television.
Can I press a button? No. Okay.
Yeah.
Thank you. Thank you very much for your very, very interesting overview of all the control in drones. I would like to ask you, our drones now are mostly under-actuated, and you have shown us many inclusive over-actuated. Do you think that the future is going to be on over-actuated, or we are going to still stay on the under-actuated? That's first question. The second question, everybody's using now the MPC, the model predictive control. What do you think about the future of the MPC for control?
Yeah. So I think they will still both coexist, the two platforms for many years, the under-actuated and fully actuated, and we will we already see also hybrid or morphable platforms that can decide what to be based on the particular task in that moment. Because there is a trade-off. Basically, under-actuated platforms are more energetically efficient, while fully actuated are better for accuracy in position. So depending on what is more important for the particular task or the boundary conditions, then one approach is still better than the other in terms of design. So I don't think there will be a selection of one or the other. But I see an increase in industry of interest for a fully actuated, which makes sense to me. Regarding MPC, so the big problem a few years ago was that computationally speaking, we were very limited to. And now that computation became much better, and also these algorithms are faster, they do better, they approximate better the solution, they can be used. And I think it's a bit like with learning. So it's a tool, but you should not give up trying to understand reality or the system, or trying to go to optimize even better the design, or just because you have found maybe a recipe that seems to work for any possible task. And still, it's very important to you need to have this insight, this understanding of your platform in terms of, because this is the only way that in which you can understand its limits, what can be used for, or how much can be pushed to its limit, what can actually do. Because you might end up trying a certain platform to do some things that are actually not possible, and not understanding why your optimization-based controller cannot find a solution, or every once in a while doesn't find a solution. And then the question is this a structural thing? Is it because my method, that my solver is not good enough? Should I work more, spend the next year improving the solver, or should spend the next year improving the platform? So it's still very important to, this is a tool, very powerful, but it's still very important to understand the physics, and even when you get a solution, try to reverse engineering it in the sense of science. So to go back to the scientific insight.
Other question? Yeah, there's a question here. It also works the other way around. Yiannis.
Okay. Case number one, you want to design the control while you have motion capture. Case number two, you don't have motion capture, but you have, let's say, a camera or some perceptual apparatus. How different are the two control problems? Are they fundamentally the same? Are they fundamentally different? And if not, what is their similarity? Because the perception will have a lot of uncertainty inside, which you don't have in the case of the motion capture.
Yes, uncertainty is just one element. The fact is that motion capture is very close. The difference between the two cases, I feel, is on this fact. The motion capture is very close to an ideal knowledge of the full state of the system that you want to control. So it's like if it's there, but it's actually not there. So the motion capture is there, but you can observe your system, your flying system that you want to control, without caring about the fact that you're using a sensor. You are like in God mode. Let's say you know the system very well, and so you have that system to control. And in that, this is a standard control problem, a system to control with dynamic equations and whatever. In the other case, you are putting a sensor that is not transparent. It has its own dynamics, its own model that enters the system in a non-transparent way, adds to it. It's connected in feedback with it. And it adds to it in terms of uncertainty, but it might even have a dynamics. Your sensor might be subject to temperature, might add states that are completely not present in the original system, might be slow in getting to that set point, might have its own dynamics, for example, or might work only in semi conditions. Maybe if the speed is within these limits and these limits, so outside of these limits it doesn't work at all, or maybe behaves not anymore as a sensor of a certain quantity, but measures another quantity. So you are not basically then in a situation in which your original system has been complexified by the addition of another system. So the system that now you want to control is different. And so the controller is different. This is the reason why. And you have to consider a different system in the two cases. So then if you really want to make things work in a real world, you need to finally consider this more complex and global system. Motion capture is helpful to have a simplified version of what will be the real system outside of it, but doesn't bring you up to the point in which you can really rely on the results that you get just with motion capture. But the real difference is this, I think, is that and the answer to your question is control will be completely different because the sensor just changes the system. It's not anymore just the simple robotic platform. Yeah.
Okay. Is there still a final question? or shall we leave the discussions for the coffee break? So if there's no burning question anymore in the audience, and let's thank Antonio again for the fantastic talk.
Thanks. Thanks.
So we now have a half an hour coffee break, and then we come back here for the last session of today.
Don't you want me? You know I don't believe you when you say that you don't need me. It's not too late to find. You think you've changed your mind? You'd better change it back, or we would both be sorry. Don't you want me, baby? Don't you want me? Oh, don't you want me, baby? Don't you want me? Oh, I was working as a waitress in a cocktail bar. That much is true. But even then I knew I'd find a much better place, either with or without you. The 5 years we have been such good times. I still love you, but now I think it's time that I live my life on my own. I guess it's just what I must do. Don't you want me? You know I can't believe it when I hear that you won't see me. Don't you want me? You know I don't believe you when you say that you don't need me. It's not too late to find. You think you've changed your mind? You'd better change it back, or we would both be sorry. Don't you want me, baby? Kicking around on a piece of crown in your hometown, waiting for someone or something to show you the way. Tired of flying in the sunshine, staying home to watch the rain. You are young and life is long, and there is time to kill today. And then one day you find 10 years have gone behind you. No one told you when to run. You miss the starting gun. And you run to catch up with the sun, but it's sinking. And racing around to come up behind you again. The sun is the same in a relative way, but you're older, shorter of breath, and one day closer to death. Every year is getting shorter, never seem to find the time. Plans that either come to naught or half a page of scribbled lines, hanging on in quiet desperation is the English way. The time is gone, the song is over. Thought I'd something more to say. Home, home again. I like to be here when I can. And when I come home cold and tired, it's good to warm my bones beside a fire. Far away across the field, calling on the IMAV, calls a faithful to an hear the softly spoken words.
You're the last speaker, right?
I am
Sing with sound.
Yes,
No?
okay.
Yeah, okay, that's your thing. Okay, I'll be the chairman.
Fantastic. I've already checked the laptops.
Perfect, thank you very much.
Thanks, Muhammad. I was forgetting it.
No problem.
In this room, in this skies of snow,
You need anything?
Like a clicker or something for the next slides, or should I just do it?
I'm not sure if there is anything. Everyone is using. There's this one.
Yeah, I think it's this one.
You need to plug something in, maybe, or not?
Or maybe it's the power button or something. Well, then I just use this.
Hello everyone, welcome again and good afternoon. So my name is Murat Bronz, I'm from INAC, French National Civil Aviation School. I'll be chairing this session related to perception. And for the next 75 minutes, we will have 5 papers related to perception again, and they will be related to actually how we can improve the performance of an existing visual odometry algorithm. And then the next one is in a rainy and foggy situation, how can we use the single pixel imaging? Then we will be working on the pitching oscillations and trajectory oscillations as well. And the last paper is going to be related to the seeing with sound. So without further ado, I'm giving the floor to Bahnem.
Thank you for the introduction. My name is Stavro Bahnam. I'm a PhD student at the Micro Air Vehicle Lab of Delft University of Technology. And today I will present to you improving the computational efficiency of Rovio. I did this work together with my supervisors, Dr. Christophe de Wachter and Professor Guido de Kroon. Rovio is one of the state-of-the-art monocular visual inertial odometry algorithm that is running on has a lightweight computational cost. But what is actually the visual inertial odometry? The goal of visual inertial odometry is to estimate the position, velocity, and attitude of a vehicle using a camera and IMU. Well, this is actually interesting for micro air vehicles because it allows it to operate in certain environments where other sensors do not work. Like, for example, in indoor in indoor areas where, for example, GPS does not work. Think about greenhouses, but also indoor autonomous drone races. Furthermore, the sensors are relatively low cost, and it fits the micro air vehicle, like the size, weight, and power restrictions. So Rovio stands for Robust Visual Inertial Odometry. What Rovio does, it uses an iterative extended Kalman filter that jointly optimizes the feature location with the vehicle states. And it uses direct photometric feedback to update those states. So what is actually the direct feedback that I'm talking about? Well, for the measurement, it takes every pixel for every feature, it extracts a patch, and it takes the difference of the patch on the previous frame with the predicted patch on the next frame. And the Jacobian is constructed with the gradient. And additionally, it uses some parameters to compensate for the change in lighting conditions. What the problem actually with Rovio is it's an iterative extended Kalman filter, and the number of states expand rapidly with the number of features that we want to track. It has 21 vehicle states, which are the position, velocity, and attitude of the robocentric frame. And it has also the IMU bias included, which stands for the gyroscope and the accelerometer. And additionally, the IMU and camera instrings, the translation and rotational part. The three states, from the features are a 2D bearing factor and an inverse depth. So why is the problem that the number of states, what's the problem if it increases? Well, the prediction step and the update step of the iterative extended Kalman filter, the computational cost grows rapidly with it, because you basically increasing the matrix size and therefore also the computational cost. Rovio pre-integrates the IMU data and does the prediction step only once for every new consecutive frame. And actually what we found is that actually from the prediction step, the covariance calculations is the computational most expensive part because it includes the system matrix F dot the previous state covariance matrix. Yeah, like as you can see, like on the screen. Well, we can solve this problem actually, like if you look more into detail, like what is in those matrices. Because the system noise, the system matrix F is actually very sparse. Like in red, I'm indicating all the zeros, and in green, all the non-zero points, non-zero indices. And actually, we can do the same for the G matrix, the system noise matrix. And actually, W, the system, the input noise matrix, is actually just like a constant diagonal matrix. Exploiting this information, we can save a lot of computational time without actually losing the accuracy, because we're still calculating the same thing. However, the main computational efficiency gain, we can gain it from the update step, because the update step runs like on every frame for every feature separately and multiple iterations, because it's an iterative extended Kalman filter. And again, like what we actually should know is like what Rovio does. It calculates the Jacobian, which is a 2x2 matrix, basically like kind of the image gradient of the patches, and followed by a QR decomposition. But like it gets like a 2x2 matrix, but it inserts it in a 2x(n) matrix. Here, H is the Jacobian, and P is the covariance matrix from the prediction step, and R is the measurement, the update noise matrix, which is 2x2 matrix. So as you can see, like here, H is like got a lot of zeros in there, and only contains a 2x2 matrix that is non-zero. Therefore, we can like reduce the whole matrix multiplications just by a 2x2 times another 2x2 times another 2x2, and then add like the noise input matrix. And like with thinking in mind that like actually the Jacobian is a 2x2 matrix, we can do the same thing for the Kalman gain step calculation and the update factor. We tested the original algorithm and the modified algorithm on the Euro dataset, also on the FPV drone race dataset, but like today I just want to like talk about the Euro dataset, and we expected to have like the same accuracy as the original Rovio. Oh, I'm sorry, I missed something. Like first I want to show you like what the computational gain, like what we actually gained here. Like the original algorithm required 25 milliseconds on a Jetson Nano NVIDIA TX2 on average like to process one frame. Well, the modified algorithm only required 15 milliseconds. So we gained a computational efficiency of 40%. Well, we expected that the accuracy would be the same for the original and modified algorithm. Well, that turned out to be for like those sequences. But for some sequences we saw like a difference. But what we also noticed, like once we were like analyzing the differences, we saw that we also saw like when we run it on a different device, for example on a laptop, we would also get like a different value for the original algorithm on a TX2 or on a laptop. And often it also matched with a modified Rovio on the TX2. We found that it was actually like a machine rounding error. But then the question is like, well, a machine rounding error, how can it influence that much of accuracy? Well, for that, actually, like, I want you to have like a look together at Flight Room 203. At the here on the y-axis, I'm plotting the absolute position error of the modified algorithm and the original algorithm, and on the x-axis, I'm plotting the frame that we are processed. We see that we up to the 1000th frame, we're having the exact same position estimation, and after like a certain frame, it starts to deviate. When we have a look at the 1006 frame, we can see that we are tracking exactly the same features for the modified and the original algorithm. However, with the next frame, we see that one feature in the modified algorithm is labeled as not tracked, whereas for the original algorithm, it is labeled as tracked. And the reason for this is just like the feature is just at the border, and like if the corner like just goes outside, then it says like, okay, the feature is outside of the frame, and therefore we label it as not tracked, and it will discard that feature. But then still, like, how can one feature like change the accuracy that much? The reason is like because Rovio detects only new features when the total the total tracked features is dropped below a certain threshold. Therefore, in this case, the modified algorithm starts to insert new features earlier than the original algorithm. And if we look like about like 100 frames later, we are tracking totally different frames. We are tracking totally different features, and that will cause the difference in accuracy that we get from the modified and the original Rovio. However, like we're doing exactly the same calculations. It just like stems from the rounding error. So just to conclude, we reduced the computational cost of Rovio by 40% by just exploiting the sparsity of the matrices in the prediction step and in the update step. This resulted that the computational cost is way less dependent on the total number of features that we want to track. And the code is open source available, yeah, which you get like hopefully like if you want to use Rovio, check it out, and I'm happy to help you with that. Yeah, if you have like any questions, feel free to ask them.
If you have any questions, I can give you the microphone.
Do you know if there is any other ways of improvements, other parts of the equation that you can simplify? And what would be the, because here you are not losing anything, except that sometimes the tracking seems different. But if you accept to lose some accuracy, can you gain something?
Yeah, so like, if I understand your question correctly, like you're asking like if we could like gain something from this. And I would say like yes, like you're reducing the computational cost, therefore you're reducing the latency of the system. And like actually in real-time systems, like how faster you can process the images and the VIO, the lower like actually like error you're gonna accumulate. Like in a VIO, usually like you predict your position and velocity and attitude, and in the time that you don't have like any values of that, you just integrate your IMU data. So by doing this, like you're reducing the time that actually you have to integrate your IMU data, just so like you get like a more, hopefully like a more, yeah, a better trajectory following drone. Or like, yeah, you could add additional things. For example, you can track more features because now it's less dependent on the number of features that is tracked. In the original Rovio, the number of features is just like limited to 25 because of this reason. And now you could like, for example, change the settings to, I don't know, 50 features or 100 features just to be more robust. Does that answer your question?
Any other question? One myself. It's related to if you run the algorithm, like, let's say 10 times or 100 times, are we always selecting the same features?
Yes, if you also make sure that they also initialize on the exact same IMU data, basically. But like, yeah, for running those tests, I checked that they run, that they both start like initialize on the same timestamp, and I run them also multiple times. Like it doesn't vary.
Okay.
If you also of course, process all the frames and don't drop them
Mhm.
because you're processing too low, too slow.
Okay. Thank you, Bahnam. So we will switch to the next presenter, Carlos, if he is here. Okay. Carlos is not here. Then, no.
Someone in the audience knows whether he's there. Ask the audience whether someone has seen him.
From the audience, is there anyone who knows Carlos Osorio Cuero from Mexico? No. Okay. So then maybe we can switch to the third paper. Ilya? Okay, you're here. Okay. Luckily and hopefully the third presenter, Ilya, is here with us. He will be presenting his paper, Handling Pitch Variations for Visual Perception in MAVs.
Yeah, I think we do have Carlos here online. We're going to try to get him online.
Okay.
Yeah, sorry.
In a sec.
Okay, should we then switch to the second one again?
Yeah, if they're
okay.
online.
Okay. I'm sorry for the confusion, Elia.
Okay.
So apparently he is online, so he will be presenting. Sorry again.
We thought all the remote ones were on Friday.
Mhm.
Not today.
Okay. How is he going to connect from upstairs? There?
Yeah, they're working.
Okay. Sorry. At least you will go out 2 times.
You didn't see the microphone that I should use? It's the one on the...
There's another one if you want to use handheld. Otherwise, this one is also working.
Because I think it was switched off right now.
Yeah, whenever you need to use, they are switching it on.
I'm going to check.
Sure.
Just a matter of putting it on the screen, I guess. So, but I will quickly check and then I'll come. Okay. Yeah. So we should swap. So we should go back to the third speaker.
Okay, by apologizing again, we want to take you again to the stage.
This time will be
Yeah, it will be the real time. The other one.
also this one is turned off. Test? Okay. Yeah, this one seems fine. Okay. Hi everyone, I'm Elia Cereda with the Aloimonos Institute of Artificial Intelligence in Lugano, and I'm presenting today this paper on handling pitch variations for visual perception in MAVs, synthetic augmentation and state fusion. I think I don't need to tell you, intelligence and autonomy are such important topics in unmanned aerial vehicles to unlock their true potential. And in my group, we have been focusing in particular in the last few years on very small robots and bringing this kind of autonomy on such a low scale, which allows you to achieve capabilities to safely fly in human proximity and interact with them. As you move down to such a small robotics platform, also the computation power that you have on board it becomes really constrained, in particular on this kind of devices. The only computation capabilities that you can afford are small microcontroller units. So traditional robotics frameworks such as localization, mapping and planning is something that is not really viable on this kind of devices. So an approach that we have found being quite successful is to employ this kind of reactive methods based on CNNs, where a CNN directly takes a visual input and produces a perception estimate that is directly used to then control the robot. This works really well because with CNNs it's possible to scale models so that they match the resources that you have available. One example of this approach has been this pulp frontnet, state-of-the-art convolutional network for human pose estimation on a nano UAV. Here, the task is to estimate the relative pose of a person with respect to the drone using just a single low-resolution image that is acquired directly on board. The target platform that we use is the Crazyflie by BitCraze, and specifically the GAP8 system on chip on the AI deck. To solve this task, we have been designing this convolutional neural network, a custom architecture that is able to achieve a throughput of 48 frames per second using just 96 milliwatts of power on this tiny platform. Unfortunately, delivering this kind of methods in a real-world application is far from trivial. And in this work, we have been focusing in particular on one specific challenge that we have been encountering, which is the variations in drone attitude during flight. As the drone moves back and forward, the pitch of each camera changes continuously, and this strongly influences the images that we acquire, as you can see here in the video. To make matter worse, during flight, the distribution of the pitch is very biased towards zero, so it's hard to acquire samples at a strong pitch. But on the other hand, in those situations, the drone is strongly accelerating. So making an error in perception in those conditions can have a strong effect on the control of your drone. We would like something more like this, a uniform distribution where we have images from the entire range of the pitch. This can be framed as a problem in the course of dimensionality, something that quite often happens with highly dimensional data, where a large variation in the appearance of the image doesn't have any impact on its semantic content. And a model that should process this data needs to learn how to ignore these variations. Some approaches to deal with this problem, for sure, stabilization. In larger drone, gimbal or digital stabilization algorithm allow you to get images that are always almost at a constant pitch, despite of how the drone is moving. But the complexity of these methods to this date prevented using them on a nano drone. Another approach would be to ensure that the model directly learn the desired invariants from the training data. Something that we have seen with real-world data is not really feasible because of this bias distribution. But in deep learning, a very common approach is to use data augmentation, where you randomly perturb images, real-world images, using these synthetics variations that increase the variability of your data. And this has also been proven previously in one of our work, and it's very affordable on a nanodrone since it's only impacts at training time. The third approach, in an orthogonal direction, is to give additional information to our model that helps it understand, basically simplifying its task. And in this paper, we have been focusing on two methods based on these last two approaches. The first is a task-specific data augmentation strategy that generates multiple synthetic views of a single training images at different pitches by cropping a horizontal slice of the image at a randomly varying vertical offset. In this way, we trade off the vertical field of view of the camera for a greater variability in the pitch, as you can see here in the images and also in the distribution of our training set, which becomes much more uniform than before. On the other side, the second contribution is a way to exploit the estimate of the pitch that we already have on board from the state estimation to give it as input to the neural network. In particular, we propose an extension of the architecture which takes this new input, processes it, and then fuse it with the feature that we get from the convolutional visual part of the network. We evaluate the effect of these two approaches on a test set where we measure the regression accuracy of our model using the R2 score metrics, where 0 is a regressor that always predicts the mean of the data, and 1 is a perfect model. And we can see that pitch augmentation has a drastic effect across the entire range of the pitch. In particular, it makes the performance much more stable at high pitch. The vision state fusion technique is really helpful on the Z component of the output, where, which is reasonable given that it's the component most influenced by vertical displacement in the image. And luckily, the two techniques can also be combined to achieve the top performance and best possible system. Next, we evaluated the effect of these models in a closed loop experiment. Here we measure the control performance of the entire system with execution happening entirely on board. We have the drone autonomously approach the human subject and position itself 1.3 meters in front of them at eye level, as the subject first stands still and then kneels to stress the model along the X and Z directions. We quantify the effect with these plots, where we compare 30 test flights over 3 different subjects. And you can see here in the horizontal and vertical components of the error over time as the drone approaches the person. And note that in the vertical axis, we have 0 at the target altitude to deal with subjects with different height. So you will see now in a moment why this is important. Here, we see that the stateless model struggles to track the subject both horizontally and vertically. And when the subject kneels down, as you can see, the error in the vertical direction goes up because the target position is moved. The stateless model is not able to go back and converge again. While on the other hand, if we see the stateful model, we see that it's able to continuously track and it has no error in the horizontal distance, while on the other hand, in the vertical direction, it's also able to converge back to the target by recovering the error as the subject kneels down. To conclude, we have seen that these changes in the drone attitude are a challenge to CNN-based visual perception methods, which can be dealt with using these two approaches, pitch augmentation and vision state fusion. The first, it's especially important to stabilize performance far from the neutral pitch, while the second, it's an especially strong effect once you see the closed loop performance, when the prediction of the model are used to actually drive the behavior of the robot. And with this, I conclude my presentation, so I would like to thank you for your attention, and if you have any questions.
Thank you. Are there any questions?
Thank you for your presentation. You said that computational power is a hugely limited resource on the drones that you use. How much effect does pitch augmentation have on that computational resource that you have?
Yeah, one of the main benefits is that as a data augmentation technique, you apply it during the training of the neural network. So it happens on a server with a GPU. You are not constrained in computational power. Then the final model that you get runs on the drone exactly the same. You don't need any changes to benefit from this. On the other hand, the second technique using visual state fusion. Excuse me. Okay, this one. Yeah, in this case, we have this small extra part of the network that processes the state, which even though it increases the computational load, it's only a small cost. It's only 0.5% of the entire network because it processes a single input.
Okay, thank you.
Thank you for your question.
Thank you for the very interesting presentation. I have a question, but first, to confirm, also for example, these deep nets that estimate depth, pitch angle is a big problem. So most people train on Kitty, but on a drone, when you pitch, and and this is indeed data augmentation, is a smart idea. My question is, perhaps I missed that, but how do you train this network? Because it's like convolutional, right? So it goes. How do you make the data set in the first place? So you have a sorry.
Okay, I think I understood your question. Basically, here you have as an input an image from the camera, and as output the 4 numbers that represent the relative pose. We train this using supervised learning. So we have a data set that we acquire in a motion capture room, where we track both the drone and the person as they move around. So we acquire a training data set that then gives the ground truth data that we want to get from the model.
Okay, clear, smart, by the way, because you get it from the motion tracking system. And how far do you think the network is tuned to the space in which you do this? Because it's
this is also a big problem. We have been trying to tackle it in this small reference that I left here. This was the first time that we tried to do this kind of task-specific data augmentation. We got big success. It was especially for dealing with the generalization. So we were doing a randomization of the background in the image to exactly deal with the problem that the actual data is always acquired in a single lab, because you need the motion capture system. So in this case, we replace the background with the random images using another CNN, already existing one, the Mascar CNN. It will give you the position of the person so that you can then eliminate everything else and replace it with a random image.
Okay, very cool. Thanks for the talk. Yeah.
Thank you.
Thank you very much. I have been told that Carlos is still not online, or we are having a connection problem, so we will be switching to the 4th paper. Next presenter is Lucia. You can take the floor, please. She will be presenting her paper using trajectory oscillation timing improves in flight odometry based solely on optic flows.
not sure. Oh, yes, okay. No, definitely not. Yes, okay, sorry. I have to understand how it works. So, hello everybody, and I am Lucia Bergantin from Aix-Marseille University, and I'm here to present you our latest work, which is based on, which focuses on visual odometry based on optic flow. So, today I'll start talking about the problem of navigation in an unknown environment. I'll then show you some previous results that we had. I'll then speak about the three visual odometry methods that this work focuses on. I'll then show you the comparison of the three methods. Then I'll be talking about some preliminary results that we have for outdoor tests already. And then I'll conclude and talk about more future work. Okay, so navigating in an unknown environment is a problem for every kind of robotic application. But when we speak about drones, especially micro and nano drones, well, we have some extra constraints linked to size, weight, and power. And so from all this stems the importance of using minimalistic equipment that kind of fits into not all these requirements. So there are a lot of previous studies that talk about visual odometry. So we have probably the most popular technique is SLAM, so simultaneous localization and mapping. But there are others such as EMU-based dead reckoning and so on and so on. So an example of SLAM, for instance, we have over here. So we have in blue the estimated trajectory flown. So it's taken from this particular study, so Fassler and others from 2016. So in blue, as I said, there is the estimated trajectory flown, and at the same time, we're able to reconstruct this indoor scene. So one of the great things about SLAM especially is that it tends to be really, really precise in general, but most of its techniques are actually based on the use of cameras and very complex algorithms, and they require a lot of computational power, especially because they have a lot of feedback from the environment. So there is this concept of localization that is constantly recalibrated from the mapping. Well, it depends a bit about technique, but that's kind of a gist. And so what we propose in this study is actually an alternative technique that is only based on the use of optic flow sensors and that does not require any feedback from the environment. So we don't use any beacons or any mapping and so on and so on. Okay, so let's consider the case of I was expecting to have like a laser pointer or something, but let's consider this case like this. So we have a drone. Well, we have an accelerotor because in our case we use an accelerotor, but it is equipped with two optic flow sensors, as you can see in blue. They're set at an angle phi and minus phi with respect to the vertical of a drone, and each sensor is perceiving an optic flow magnitude omega phi or omega minus phi. The drone is actually flying at a distance h with respect to the ground, so a distance over that, and a velocity v, and it's flying forward, and at the same time is oscillating up and down. So why this particular trajectory? Well, because this technique is actually inspired by winged insects, more specifically by honeybees. But well, over there you can see an example, this GIF of a butterfly, actually. It's more clear. So as you can see, winged insects, they do not fly in a straight line, but they kind of go up and down. So they go this kind of oscillations like this. And this is important because this adds information on the optic flow vector field. So there's this oscillating, this up and down component. So it's sort of a zoom and dezoom of the optic flow. So the forward trajectory just gives us the translational optic flow Q. So it is that pattern over there in red, that you can see in both cases. But when the insect is up, for instance, so it's farther from the ground, there's sort of a dezoom of the scene. So there is a contraction in the optic flow vector field. While when the insect is closer to the ground, there is a sort of zoom of the scene, and so there is an expansion. So a series of contractions and expansions can actually be quantified as the optic flow divergence Q. And it is sum on top of a translation optic flow. And so what we get at the end is a translation optic flow that you can see in light blue at the end. So let's go back to the drone. What actually we proved what we proved mathematically in previous work is that the translation optic flow can be measured as the sum of the two magnitudes that I was talking about earlier, divided by a given factor, as you can see in equation number 1. And the divergence can actually be computed as the subtraction of the two magnitudes divided by a given factor. And what is kind of neat about this oscillations is that due to this oscillations, due to their presence, the distance from the ground h and the velocity in the same direction, so vh, vary, so they are observable, and so we can use the divergence to observe them, so to observe a state vector. And on this concept is based the model of a visual odometer that we presented in this particular study over there from 2021, in which we propose to do visual odometry over the longitudinal axis, so the x-axis over there, by integrating over time the translational optic flow multiplied by a scale factor, and this scale factor is the estimated distance from the ground, estimated by means of extended common filters that receives as measurement the optic flow divergence. So the first method that I'm going to talk about today is actually like a straightforward application of this visual odometer. And it is based on no prior knowledge of the optic flow variations. We only use two optic flow sensors along the x-axis, as I've already described. And so we compute the translation optic flow as the sum of the two magnitudes, the divergence as their subtraction. We give the divergence as measurement to an extended common filter. The common filter receives as inputs the acceleration over the vertical axis. So thanks to all this information, we can estimate the distance with respect to the distance from the ground. And then we can use all this in our visual odometer. And when we tested this on the accelerometer, this actually works, but the optic flow cues that we are able to measure actually present a lot of noise and some peaks. I'll show you an example later to explain, but this can be improved. That's more of a concept. So we move forward towards this kind of configuration with 4 optic flow sensors. Well, the optic flow sensor we're using are actually from BitCraze. So we have this 2 optic flow sensors along the x-axis that are the same ones that I've already spoken about, and then we have like an extra pair over the lateral axis of a drone. And so the idea is that with this configuration, we can actually measure 3 translational optic flow cues and 2 optic flow divergence cues. And so the idea is that we can add 2 extra common filter, one to filter the divergence, receiving as measurements the 2 optic flow divergence cues measured, and one to filter the translational optic flow cue, receiving as measurements the 3 translational optic flow cues measured. And then we use the same technique. What is still an open question at this point is like, what do we use as inputs for the common filters, so that UDIV over there and that UT down there. So the first solution that we came up with is actually based on the use of a precise prior knowledge of the optic flow variations. So the idea is that in our tests, we impose a certain trajectory on the accelerometer. And so we know the oscillation amplitude, the oscillation frequency, and the initial distance from the ground. And so thanks to all of this information, we can actually come up, we kind of know how the optic flow cues will look like. And so we can come up with very specific, precise models. So one for the optic flow divergence in equation number 4, and one for the optic flow for the translation optic flow in equation number 5. So to give you an idea, well, what we get from equation number 4 is this oscillating signal, which is fairly specific because it has like a given amplitude, and this, well, I cannot really point it out, but this distortion over here, which is very specific, so it's not trivial. So thanks to this method, we actually managed to increase the signal-to-noise ratio, so that was good. But still, it is based on a lot of information. So we actually move forward to a method that is based on a rough prior knowledge of the optic flow variations. So for both optic flow cues, we used the same model that you can see in equation number 6. And the only information that we have is the oscillation timing. And so what we get is something like this. So it is an oscillating signal like that. And the only thing we know is the oscillation frequency. OK, so I'll show you just a brief video. That does not start, which is weird. Okay, yes. So over there, you can see the accelerator flying this kind of bouncing circular trajectories. Over there are the optic flow cues that we measure. So in red, the translation optic flow, in blue, the divergence. And at in the bottom, you can see in dashed line, the estimated distance from the ground. And in continuous line, there is the ground truth given by the motion capture system, so like a beacon system of a flying arena. And this particular data set was actually processed with rough prior knowledge strategy. So we took 14 data sets at a low illuminance of 170 lux and at a high illuminance of over 1500. And we processed them all with all three methods. So to compare the three methods, let's consider one data set taken at high luminance and process it with the three methods. So let's start with the NPK, so the no prior knowledge method. So as you can see, we're actually able to compute the two optic flow cues fairly well, but there's still quite some noise. And there are these kind of peaks. I've highlighted some here and there, but there are more actually. So it's good, but not too much. So when we use the divergence to estimate the distance from the ground, that you can see that in a continuous line and compare it to the ground truth given by the motion capture system in dashed line over there, well, you can see that yes, it does follow the same trajectory, but there are some errors here and there, and could be more precise. And so when we compute the error, the percentage error of the estimates with respect to ground truth, well, we get some peaks in the error here and there. And so the final percentage error of visual odometry, which is sort of what interests us, actually, is this minus 8.6%. So it gives us a rough idea, but it could be better. So when we process the same data set, the exact same data set, with the precise prior knowledge method, we have a complete different story. So we're able to, we have way less noise. So we virtually have no peaks on the divergence. So we have those two very small ones, but they're really no big deal. And then we have fairly bigger ones for the translation optic flow, but still okay. So the estimation of the distance with respect to the ground is much more precise, and so the percentage error is reduced, and this reduces drastically the percentage error of odometry, which is down to 1.2%. And we have fairly similar results with the rough prior knowledge method. So basically the same thing for the optic flow cues. The estimation of the distance from the ground is good. And we have a slightly higher percentage error of the odometry, which is minus 2.8%, but it's still way lower than for the NPK strategy. So, and we have very similar results for all data sets taken. So just to give you an idea of what we're up to at the moment. So we've performed some tests outdoors in this kind of environment. So here we have no control of the contrast on the ground, which of course we have in the flying arena. And of course there could be wind. So we took a few data sets and this is what we get. So, more specifically, these data sets were taken in a straight line. So they're kind of different from the others, also in that sense. So we processed this one data set, so here is an example with the rough prior knowledge method, and as you can see, well, it works pretty well, and we have a final percentage error of 4%. So just to conclude briefly, in this study we show that the fusion strategy is allowed to measure the optic flow cues more reliably, even when considered just the oscillation timing information, so just this. And this directly improves the odometry performance. As for future work, we need to test the three methods in a wider range of forward speeds, drone pitch in the presence of reliefs, and of course, a little bit more outdoors. And we're also planning to go more towards an autonomous application, so to have the drone coming back to its own base just on this technique. So, well, I'm done for today. Thank you for your attention, and if you have any questions.
Thank you. I can take one question.
Hi, thanks for that. That was really good. Do you have any feeling for like how the frequency and the amplitude of the oscillations affect the accuracy of the measurements?
Yes, definitely. So thank you for the question. It's very good. So the frequency does not really influence too much the outcome, but the amplitude does, actually. So we need fairly big amplitudes for the moment. We're working also on a system that would be just on the drone and just the system oscillating by itself. So we're kind of going in that direction. And maybe with cameras also we could really reduce the amplitude. But for the time being, with optic flow sensors, we really need big oscillations.
Thanks.
Let's thank our speaker again.
Thank you.
So still no Carlos. That's why we will be continuing with our fifth paper. Simon is going to talk about seeing with sound.
But I just asked, and they told me that it's still down.
Is this the one that's working?
No.
Nope. That's not the one that's working. What about this one? There we go. Hello everyone, I am Simon Wilshin. I am Richard Bomfrey's postdoc at the Royal Veterinary College. There are many ways to make a talk interesting. You can invoke Chomsky, you can talk about quotes from Carl Sagan and Einstein as we saw earlier. I'm late in the day, so I'm going to appeal to the cheap seats. We're in the Netherlands, I'm going to make fun of the Germans. So, this is where we are. Around here, they speak Dutch. I am from the United Kingdom. We speak Island Dutch. Unfortunately, there are some differences between the two. A major notable one being that there's no phrase that adequately conveys in Island Dutch the notion of working together with other Europeans. We also have over here Mountain Dutch, and finally Plains Dutch. This is an alleged language, but no one from this region actually talks, so we don't actually know about that. You can tell I'm not actually Dutch because I made fun of the English before the Germans and business before pleasure. Now, if you speak both English and German, Island Dutch and Mountain Dutch, you can read Dutch signs. Your visual system is capable of interpreting the environment and getting a feel for what is going on in terms of the train or bus timetable that you're seeing here. You can't, however, speak the language, and so you can't hear things and interpret your environment. This is a very similar situation to the one we find ourselves when we're working with drones. We have very good ways of visually identifying things in the environment, but we're not so great when it comes to auditory systems. So, multimodality, that is the ability to do things like hear, sense pressure, sense temperature, sense the visual environment, builds redundancy and adds information. And I've got a couple of examples of that. So we do work with visual systems at the RVC, but I'm going to be talking about the system that we've got in the bottom right-hand corner there, which uses microphones. So to give you two examples of this, I've created some sophisticated simulations of two visual environments that are difficult to work with. So this is a simulation of a large, planar, diffusely lit surface, and I want to move towards that surface and generate the optical flow. And so you can see this is the first frame that we've got to work with, and this is the second frame. It's kind of hard. Now I have a second very sophisticated simulation. This is a much more complicated environment. There's lots of objects in there, but it's dark. So in this one again, you take two frames in succession, it's difficult to see. I'm not saying that visual systems aren't important. I'm saying that having multimodality lets you deal with circumstances that are potentially difficult. So what I want to do is take a drone like the Crazy Flight that you're seeing here, or our in-house drone that is slightly beefier and larger, and I want to find planar surfaces in the environment by listening with microphones. So the surface might be further away, it might be at different angles, and it might be below the drone and again at different heights. How am I going to do this? Well, I've got microphones, 10 of them on the drone. The problem with this is that we're doing something similar to using sonar, but if you're on a submarine, you've got an engine at the back and you can locate the hydrophones at the front, away from the loud engine noise and the interference that generates. That's not something that's as readily doable on a drone, because that's where your engines are, they're everywhere. However, you do have the advantage that you don't have to generate a ping, because you can use the noise generated by the engine and its reflection in the environment to inform you about where surfaces are. And so that's our strategy. So this comes in 3 stages. The first stage is we have an anechoic chamber. So this is a chamber that is coated in foam that's specifically shaped to reduce the reflection of sound. You can see on the right-hand side there, we've got a boom that has a surface on it that we can adjust the position of. The surface can also be placed below the drone. In this instance, the drone is in a fixed position. We power up the engines to achieve the equivalent thrust to hovering, but it's obviously tethered here. And then we record the microphones. And what we want to know is, can we determine where this surface is based on the recordings that we get from those 10 microphones. So this is tethered. This is the tethered example. We're going to move on to free flight and a dynamic avoidance of surfaces later on. But for now, how do we do this? Well, we had a talk earlier that mentioned the problems with neural networks. I think that that's a very fair perspective to take. The virtue that you have is, of course, that you can get quick answers and you can determine if things are possible relatively easily with a neural network. We have recordings from 10 sensors. We're also going to feed into the neural network their frequency component. This is because we're not just doing a naive approach to the neural network. We're also, in collaboration with folks at NRL, looking at what kind of physics-based algorithms you could use. And they are looking at things like cross-correlation and other factors that are heavily influenced by the frequency profile of such a system. Now, we take those recordings, and sorry, I've gone one too far there. So we take those recordings and we're feeding them through 2 sets of networks that are combined at the end. So we have convolutional layers and then 2 fully connected layers at the end that combine the frequency information and the pressure recordings from those microphones. So we've got 200 microseconds of observations that we're feeding in at a time. It would probably be better to be using a recurrent neural network. This is our first pass at attempting an analysis. We've also thought about using something like a recursive network, long-term, short-term networks. But for the time being, this is the analysis we're going with. How does it do? It does pretty well. So this is looking at the height of the drone above a planar surface below it inside the anechoic chamber. The x-axis is the true distance. The y-axis is the network's estimated distance, so how far away it thinks it is. You've got a reasonable degree of correlation between these 2, and the standard error is about 40 millimeters. So that's not too bad. In terms of angle and distance, this is again a reasonably typical result. You do get a little more fall off with the location of the estimating the location of a wall in the environment when the plane is vertical in relation to the drone. So what you're seeing here is the drone in the center. The estimated position is plotted on that heat map and that raster plot in the background there. The true position of the wall is that black line. The typical error in the distance from the drone to the wall when it is vertical and planar is about 40 millimeters again, and you get about 15, 20 degrees of accuracy on the angle for the standard error there. So what about surface avoidance in free flight? So here what we did was we flew the drone in difficult circumstances. This was definitely intentional. We put them over a carpet so that the sound reflection would be minimized. We didn't do this because it was during COVID and we couldn't go into the lab and I had to do it in my bedroom. Any rumors to the contrary are just slander and you should ignore them. So what we're doing here is we're flying a drone. This is our more capable drone that we've built in-house. We have, again, microphones mounted to the drone, and we are recording the surface below it with two microphones, one below and one above. And what we're trying to do here again is feed this through basically the same network but with only two channels and trying to estimate the height. What we found here was that in this slightly more difficult problem, we got about 50% correct on the bottom two, which means they're not really distinguishable, and close to 100% when we were very close to the surface. So close to the surface, we were doing very well. We could detect when we were deep in ground effect, but we struggled when the drone was higher up. As I say, this is not ideal conditions, but this demonstrates that at least in terms of proof of concept, we were able to detect the surface. So what we did next was we moved on to, so I should mention why there are no vertical surfaces here. Calibration for horizontal surfaces is relatively straightforward. You can fly above the surface and you're okay. For vertical surfaces, you have the problem that you're in wall effect and you're not resisting that wall effect if you have something that is not under control. And so we weren't able to obtain data without some kind of algorithm for resisting wall effect. Otherwise, what you do is fly into the wall and then rapidly disassemble your drone, which is not ideal. So we needed to have the ability to avoid the wall to operate in that circumstance. So that's why there's no examples of trying to detect a surface that's vertical and planar without avoidance. So what about avoiding a surface when it's in free flight? Can we perform a maneuver to avoid it? What you're seeing here is me gradually dragging a plexiglass sheet up to a crazy fly that has our sensors mounted on it. The latency here is very, very bad. It is on the order of 250 milliseconds typical, up to 400 milliseconds peak. That is a consequence of how we have this set up, including the fact that we're using a virtualization system. But the system detects the surface and reliably avoids it when it's planar and below it. So this is in free flight. What about for vertical planar surfaces? This video is a little misleading. We are able to do it, but it is very unreliable. So you'll see here we bring the surface in. Eventually the drone's sensors pick it up on the microphones that there's a surface there, and it performs an evasive maneuver. The evasive maneuver is just a reposition away from wherever it thinks the surface is. It does it, but it does it in such a way that it's not especially reliable. It took a lot of fine-tuning of parameters here to get this to work. And so I would say that the previous example was successful. This one, very much less so. And so we're looking at ways to refine that, but in the interest of transparency, this is not necessarily the most reliable method for this. So with that, I will take any questions. And do we want to grab the next speaker, since we're running over time? Okay, no worries.
Are there any questions?
Thank you for your presentation. I'd like to know if the drone was flying above water. Water usually reflects the sound different of the carpet that observed. How would be the behavior?
So I think we should expand that question to what about a variety of different surfaces? Because water is going to be difficult, but especially when you're dealing with a neural network, it's very dangerous to assume that you can generalize, because it's looking for the features that it was able to identify in your training data set. And if that training data set is not very varied, if it's carpet instead of being wood, if it's metal instead of being wood, if it's water, if it's some surface that you can disrupt, if it's foam, it's going to give you different results, and it's not predictable what the behavior is going to be. So I would say if you wanted this to be generalizable, you've got two options. The first is actually understand the system in more depth so that you can predict what it's going to do, or make your training data set big enough and varied enough that it accounts for those difficulties.
Okay, thank you.
Would you say it's more profitable for observability of the obstacles that the motors are generating a lot of noise, or on the contrary, be more silent so you get a better hearing of the echo?
So I don't know the answer to that question, but I do think that there's an added interesting extension to it, which is, what do you want your motor to be doing in general? Do you want it to be operating at a fixed frequency? Do you want it hovering? Or do you want it to be presenting variable frequencies? Surely something that presented a variety of different frequencies would give you more information about the environment. We know that bats have very varied calls. And so I don't know the answer to your question. I know that if it's very loud, it clips out the microphones and then it's useless. I do know that if it's louder, it's helpful for further away. That's just basic physics. But I also know that I don't understand the intermediate condition well enough to give you a firm answer.
Thank you.
What is, thank you for the presentation. What is the minimum wall size that you used? In other words, would a much smaller item be enough, and especially, for example, a rounded tree?
Yes, excellent question. We were dealing with, I mean, you could see there, that's a crazy fly, so it's on the order of 20 centimeters by 20 centimeters in the anechoic chamber. That is under ideal conditions. It's an anechoic chamber. It's a single motor running at a fixed speed. In the second experiment, it's essentially the ground in my bedroom. It's, you know, effectively infinite as far as the drone is concerned. There is going to be a point when that breaks. When you get small enough, that's going to fall apart. I don't know how small that has to be. I would guess that being substantially smaller than, say, the rotor dimensions could be a problem, or something on that. There's some physical scale in there at which point things start to break down. And because we're using a neural network, that could even come in earlier than the physics would suggest, because it's going to stop looking like the training data.
We're still ahead on the schedule, so if you have any last questions, we can take.
How does the velocity of the proximity affects the response of the drone?
Sorry, how does the velocity of the
Approximation of the drone in the wall? Because in your demonstration, the wall was...
I moved it very slowly for a reason.
Yes.
I think that if you moved it too rapidly, again, you'd be outside of, well, in that instance, that wasn't done with the neural network. That was done with something, a physical algorithm derived from the neural network. We inspected the network to see what it was looking at and tried to adapt that to that particular circumstance. I do think that this algorithm will fail if it approaches too quickly, in the sense that it will generate a false positive for a wall moving towards it, because you'll generate a pressure wave, and that pressure wave would be identified as being an obstacle when the obstacle was further away than you thought. I don't know the precise details of how it would fail, but that would be my prediction.
Okay.
Yeah, thank you. I have a question. What was the maximum distance you ever tried in that?
So for the free-flying drones, the ones which were flying above my carpet, it was 20 centimeters. In the anechoic chamber, it was 175 centimeters. We would love to have tested to destruction there, but unfortunately the anechoic chamber is about 175 centimeters big. So we don't know the absolute maximum because we don't have an anechoic chamber big enough to test it.
Because that would be interesting for use, like outside operation, and to have it that way. But that's a long way. But I like your approach, using their own source, noise source for detecting. Thanks.
Thanks.
Question about the anechoic chamber. Would the free space not be big enough anechoic chamber?
Well, it would be big enough, but it certainly wouldn't be anechoic, right?
It is, at least
Oh,
semi-anechoic.
okay, so as in go outside.
Yes.
I see. I mean, I'm an engineer. I'm terrified of being outside. No, that is an excellent point. I think the problem you've got there is that you are dealing with wind in the environment. You're dealing with an environment that's not very well controlled. And I don't know what that's going to do to the microphones. So I think that would be an excellent way to test if you wanted to go further. I think that what would end up happening is we'd actually run into problems before we reach the maximum height in the anechoic chamber, because once you get outside of those ideal conditions, especially if you're using a neural network, things begin to get wobbly.
The steel nerves do rust.
With that, let's thank our speaker once more. And this is the end of the perception session. So now it will be Guido who's presenting detail.
Okay, so yeah, our remote presenter went so remote that we don't know where the presenter is anymore. So yeah, that's not going to happen today, unfortunately. So we'll see, we'll analyze what happened and see if we can correct it. Perhaps inserting a talk on Friday, but yeah, let's see what happened. Anyway, so that brings us to the final talk, which is a category of its own. It's an application talk, right? And we're very honored to have Professor Dieter Moorman with us, who is actually experimenting with all kinds of new use case scenarios, like the medical services, and doing tests like cross-frontier flights and things like that. So I don't want to give anything away, but yeah, the floor is yours.
Thank you very much. So we, in effect, we change a little bit the view right now, because we started with perception here, and perception is one of the things you need in order to get systems into real use. And that is what I want to talk about. And really, it was not supposed to be me, it was supposed to be Ann-Christine Sturm. She is in our group as well in Aachen University, but there was a family issue why she can't come here. She's very unhappy about that. And I also added more names, also Bart, I think Bart, I've seen him somewhere here, and Dennis, because those are projects where we show this UAS operation for ad hoc medical services, so what you need. So perception is definitely one of the key things you need for this, but there's more about, and I want to little bit focus about these topics here. And one of the projects is an CESAR, an SJU project, which will end this year. So it's a 2 years project. Safir Med is the name, innovation project for from the European Union on urban air mobility. And there were 17 different partners. I will show part of them. So Delft is part of this as well, Delft University. So how can fast, safe and efficient delivery of urgently needed medical goods become daily routine? So this is something, what is missing there. So perception is one thing, as I stated, but there are much more of them. And that this even works cross-border, that's particularly important for Europe, that we get all that sorted. What was it? The mountain Dutch and the real Dutch, that everything works together here. So I will, like the challenges addressed there, I just named part of them. Robustness is one of them, sustainability, integration into medical logistics. Some of them have nothing to do with flying itself, so it has to work, also public acceptance. And typically in these kind of projects from the European Union, a demonstration is meant, and you want to see progress in almost all of these fields. So it's a demonstration project here. And the demonstration, there was part of them in Belgium, drone port in Antwerp, all in this year. And that was, what was September 1st, so a little more than a week ago in the Maal cities. It's part of the German, Dutch, Belgium region, so that was meant to be cross-border and also on a simulation basis. So you see how such a medical service become routine. And now it's an overloaded slide, so medical transport means you have, let me try whether this, no, the laser pointer does not work. So from one hospital, you see on the left, to another hospital or a lab, on the right-hand side, and in this project, different
operator. So you see the Belgian Zapka, you see the Delft with the AED drone, you see companies like Highfly, FlyXDrive is an Aachen-based company, also a passenger drone, and all they are supposed to be part of it and have to be integrated with manned aviation, because if you're flying close to hospitals, you have to interact with rescue helicopters, for example. And all of this was then put together in a common command and control interface, and everything has to do with safety, airspace integration, so the aerodronic and Skydrone part of it, and the air traffic control of each of the countries. And that was to be demonstrated in a full setup there. This was the target of it. There's another project what Ann-Christine Sturm is heading. That's a project with little partners. It's a German project funded by the German Ministry of Transport. And this is, you see here, in the blue part, the Maastricht-Halen in the Netherlands part, and there's a German part that is due to the funding. It was German funding there, so the majority has to be in German. So you see hospitals connected, US Central part of it, where all the information is collected and coming together and integrated into a use-space services and transporting between labs, hospitals, and medical facilities, and also cross-border. So that is new to this project, but it's interlinked to the European-based project based on the results. I don't want to bother you on this slide. In fact, you see the architecture is a little different from the European project's architecture. It's more decentralized, so there will be directly connections from the use space to the vehicle itself. Not everything is going through the ground control station. So that's an ongoing discussion also in the community. What is the best way of doing, providing safety, because that's a real target, safe transport of medical goods. And there's a lot to do with data handling. So partners here it's Vodafone is doing all these issues. It's weather, which is part of it, which is part of the robustness as well that you know. And also what you see in the right lower part, I see it's German here, unfortunately, this slide. Any other air traffic which may be around. And important is the hospitals, which can be German or in this case from the Netherlands, hospitals. So they are partners there and interacting with the vehicle. So it's becoming more than just the transport. For this project, the medical transport, it's coronas to be transported. So what's in the eyes, I didn't know the term corona before, so I learned it here because that was considered as a very relevant use case from the University Hospital of Aachen together with the Zuiderland clinics in Herlen, that this is one thing. The typical transport range is about 80 kilometers. For blood tubes, it's little less. And there was an investigation on frequency, so how you want it, that's a temperature range is important. And unique is for this medical transport, it is always has to be fast, and it's not, you cannot plan it for weeks. So it's more ad hoc, spontaneous flights, and the distances are longer, and that's why we proposed for this purpose a convertible UAV. There will be a session on these kind of vehicles on Friday afternoon on this, because that is one of the things which may give support there. That's just from the FlyXDrive system, so which is giving a flight time of 70 minutes. The noise, that is a lot to do with acceptance, is low. So if it's flying in 80 meters altitude, which is a typical height, then it's a target that you don't even realize it. Yeah, and the thing is, what I want to focus on today is the air safety, the safety with respect to air, And this is the important issue to avoid conflicts with other airspace users, to detect other aircraft, and there are different systems in use, which are typical for general aviation or civil aviation right now, ADS-B, FLARM. And for the smaller system, it's more and more based on UTM systems for using so-called U-spaces, which is a setup which is built up currently in different locations in Europe. And at the end also onboard sensors, which are the most tricky ones. So that noise is also sometimes considered as one of the answers for these onboard sensors, but vision sensors, that's why we all listen very carefully, because that's a capability, and that's why we put it into these dashed lines, because it's very, very hard to find out a collision, potential collisions on this. So what has to be done if you have this technology that you are well aware that you need your data sources on this, and they can be different, so from these different systems what we know, but they have to be combined in a way that you can fly, that you don't avoid something which is not there, that you have to be really sure and have to do some data processing, tracking and filtering, and give that information to the flying system to do proper collision avoidance. And this is one of the things what you then have to do if you know where an intruder is, then you calculate this conflict geometry on this based on a consolidated situation picture, and that becomes easy if you get this information already from a UTM system or the conventional FLARM or ADS-B, that you get this information and then you follow a standardized deconflicting routing. There's some rules, so UAS always have to avoid or meant air traffic, also the direction of maneuvering is sitting there, and the latency has to be low, because typically intruders, rescue helicopter for example, they go with, compared to the UAV speed, with pretty high speeds, so the latency also is an issue. And we learned this in the perception discussion, that latency and how you get your data is always an issue here, and that has a lot to do also with conflict avoidance. And now I want to show you a video. That video is, and all Delft people will know this, and we all know this on Thursday, that's in Falkenberg. So one UAV is taking off. In fact, it's the AED drone of Delft in this Saphir Med project. And you see the drone is flying from the left to the right, and there's an intruder coming from the right. And the target is to stay within these blue limits, what you see here. And you see that the AED drone on a medical transport is avoiding the intruder traffic. You see that's a UAV 0, so it's all working with the UTM system. And the work which was done by Dennis and Bart here is that this works within a very limited space, this deconflicting operation. And that's one of the key things which were detected as very important. And now you see it's already clear of conflict. The AED drone is then continuing their transport to the injured person. So what else is there of importance? And if you have a medical service, you can't wait for good weather, so it has to work anytime, day and night. You have a way. That's whatever you use for orientation, for positioning means, has to work in all weathers. And that is why we are sure that we need different things in these. So all weather and any time. So it's always a 24/7 issue, and even that was in a campaign with the DHL parcel copter. So that was snow was one issue, but also low visibility. so that the flight system can cope with rain and snow and, for example, also icing conditions, because that's what you need, that you get a high availability of the system that shall be more than, let's call it 90–95%, so there's a typical numbers there. And the next thing is that is ground safety, and that is a current European regulation forces, for example, as if you have urban operations, to have a chute there if you fly over people, and they also have to be validated and verified according the current aviation laws, and that has a lot to do with testing. That was one test in our wind tunnel at Aachen University. And also, that is my last slide, which is the ground handling is part of it. So if you transport a medical good, you have to do something to get it to load and unload it, to charge it, and those are the key questions there. And if you just my last words now, that's the thank you slide already. In Aachen, in fact, we would have liked to fly. Also, the AED drone of Delft that was supposed to fly to a golf course from the university hospital. That all did not work, and that has a lot to do with legislation. So we simply did not get a permit. We tried 2 ways, and it didn't work out. So EASA is working hard of it, the Dutch and the German aviation authorities as well, but it did not converge this time. We hope, and that was the real aim, to show you a video of one of the flights, AED drone, a flight from Herlin, from a Netherlands hospital to a German hospital. Did not work now. We hope that we will do that in October or November this year, but it's really, really a big struggle. Thank you very much for your attention.
So thank you, Dieter. Are there questions for Dieter? Yeah.
Catch it? Thank you for your presentation. It was really good. I'm just a bit curious about how the trajectory would be made. I mean, it is to be completely autonomous, like the drone will look at the no-fly zones and the obstacles. It's all like autonomous.
Yeah, and that's a prerequisite that it is we call it fully automatic, so it will not change its idea what to do, so it gets a clear target there to go, but the way to the target is not clear. Exactly what you mentioned, for example, the no-fly zones. And that is happening in all European countries right now, that a database is set up where to fly, and that is dependent on time. For example, for nature conservation, there may be times where breeding of birds is, so you're not supposed to fly there. You're not to fly over hospitals, for example. That's one thing. We fly, that's a target here. So in fact, the regulation, and that's in fact one of the reasons why we didn't get the permit, because there's some strange things in the regulation there which we have to work on. But exactly what you said, that is one of the challenges, to have a database which you can rely on, where to fly, when to fly, and this is something which is worked on. So there's a first version available in Germany. We have one version where we have such a database, but currently this database, you don't get it in a digital format, you get it with a real map, but that doesn't help really for flight planning.
Yeah. And for sure the bureaucracy maybe is one of the biggest issues, because you have to have like authorizations for everything, and so yeah,
everything comes to the weather is, for example, something, because that is known for general aviation right now. So first you have to check the weather data, and everything here has to be automated. There's no pilot close to the location, so everything has to be automated. And the way of flying, can you really fly? So what is the wind situation? So you cannot rely this on a pilot. From my perspective, there are many challenges, and I don't know what is the bigger one, the technology one. So you know where you're at. That's what we heard this until now, the perception issue, but that's just one thing. I don't know what is the important one, but I know to have it a daily routine, we have to solve all the issues, all at the same time. And that is one of the challenges. That's what I like about the IMAV, that's what I like about the competition we will see, because that brings us towards, we get these first answers on that.
Thank you.
Thanks. Okay, is there still a burning question? And that's translated directly from Dutch, sorry for that. But so if not, then what will happen now is, yeah, first let's thank Dieter again.
Thank you.
So what we're going to do now is we're going to transfer to the aerospace faculty, to the cyber zoo. I heard that the drinks and bites are arriving already there. I also heard that there are small drones flying autonomously, so the nanocopters are in action, and they're now just waiting for us. So we have a few helpers. Perhaps Matthew, you can already stand up. So with the blue shirt. So yeah. So they will bring you there, and they will avoid the no-walk zones, right? So the red biking path is. Yeah. So yeah. So but okay, you can also use Google Maps. The only thing is that when you arrive there, yeah, it's best to just go all together, because to get to the cyber zoo, basically you need someone to let you in. So yeah, that's best. Okay. Thank you all for participating today, and see you in a few seconds again. Yeah.